Okay, let's go back to the non-stationary problems. And I wanted to do two things today. I wanted to kind of discuss a little bit this computation with the non-stationary problems that, or so-called dynamics. And then also go into the models that are more refined than simple continuum mechanics problems that are making transition to the structures. So these are like two things where the standard finite element method needs some help. And as much as it is optimal approximation property for the, let's say, quasi-static problems that are related to linear elasticity, non-linear elasticity, also plasticity with hardening and so on and so forth. Then heat transfer, which is stationary part. If you have this non-stationary part, then the finite element method needs some improvement. That's what I wanted to discuss. And also, when you make more refined models, something called the structures, where on top of the continuum mechanics, you put some kind of other kinematic hypothesis, so you can reduce the number of unknowns. Typically, you would say, for example, a beam, you say that the cross-section is such that whatever, it doesn't really deform, so that can describe the displacement. These are the particular cross-section within displacement of a particular neutral axis. And you can then kind of do the thing in a way which is more efficient, and also, for example, for place shells and so on and so forth. So all these transitions will be kind of addressed, hopefully, today. So just to recall the non-stationary problem, we first studied the heat transfer problem. This here is an energy conservation principle, where the internal energy is proportional to the heating for the, let's say, perfect conductor, where the mechanics is ignored. And we have looked into this first order differential equation, where theta is the temperature function of time. So basically, given that now the theta is both function of the space x and the time t, when you discretize, you can only accomplish half of the, let's say, solution. In other words, this is called sometimes semi-discretization, because you're discretizing by using the finite element method with respect to space. And then you come up with by using a Galerkin equation, contrary to the static problem or stationary problem of heat transfer, you do not arrive to a set of algebraic equation. You arrive at a set of a ordinary differential equation in time. So in this equation, for example, the novelty with respect to the heat conduction matrix K, that was already had to be built for a stationary problem or similar to elasticity. K would be the stiffness matrix. It appears that you have now to compute another matrix, which is the capacity matrix M. That has to be computed maybe with different type of rules, because there are no derivatives of the shape function. So, for example, you would need something like 2 integration points as opposed to 1 for K, and so on and so forth. So we studied all this, and we said, okay, when I have this system of ordinary differential equation, I studied the one such equation to start with. We can build the solution by using time integration scheme. So you can say this is a discretization in terms of the finite difference method, where you can represent the derivative as the difference between two successive values divided by the time step. This is different respect to the derivative respect to time. And you can build your time integration scheme in this way. So in particular, we studied the explicit scheme, Euler forward method, and also implicit scheme, Euler backward method. Both of these schemes are first order. That means you do approximation, which is simplified over your true variation of your time derivative. And if you want to do better approximation, you can do either trapezoidal rule or midpoint rule, evaluating the value of this at a half interval between Tn and Tn plus 1. Then we studied how to compute this for heat transfer. I'm not going to repeat this. There was the version where you compute V. This is for the explicit part. Or the version where you compute D. This we didn't know the value of temperature for the implicit part. It turned out this explicit part is much faster, given that heat capacity matrix could be diagonal, and with alpha equal to 0, this kicks out. But it suffers from conditional stability, as opposed to the implicit method that have unconditional stability. That means you can take any time step size and still have a meaningful solution, which is not the case for the explicit method. The time step has to be limited to this parameter lambda divided by lambda in particular. So basically, it turned out this lambda has a physical meaning when you go to set of equation. You can then diagonalize this system of matrices K and M. You can compute corresponding eigenvectors and eigenvalues. So lambda i's are nothing but the eigenvalues. And typically the eigenvalues have the smallest and the largest. And if you have very large difference between smallest and the largest, the stability of the scheme is set by the largest eigenvalue. That means that you have to use a very small time step, even if you really don't care for particular low frequencies. But if you keep those high frequencies, they oblige you in order to keep stability to do that. So you look into this in detail, and I'm not going to repeat it. There also consistency saying that these two Euler schemes are first order and the other one is second order. So what I want to do now is take the same consideration and look into another time-dependent problem, which is mechanics. So basically, to finally come here, if I look into a time-dependent, let's say equilibrium, this is in the spirit of D'Alembert. You can also call it equation of motion. That would mean that you have to take into account inertia effects. In other words, the loading is applied so quickly that the body moves very fast, and you can no longer pretend it's a static loading, so that the inertia effects could be ignored. So this time around, instead of saying that displacement is only a function of x, the space coordinate, you have to say that displacement is also a function of t, and the loading is, of course, a function of t, or if it's distributed, is both a function of x and t. Imposed displacement is function of t. One case of imposed displacement with the earthquake, for your structure, the base support starts moving because of the earthquake, and then you have to kind of take into account what happens. Or applied traction could also be time dependent and so on and so forth. So basically, the idea is that instead of an equilibrium equation, we appeal to the second principle of Newton, or basically that you say the force that is applied to a certain body, that is here the force is external force F, and the internal force, this is derivative of the stress, the sigma dx, is both of them are driving eventually the acceleration for a particular body. So acceleration in the local version is computed as a second derivative of the displacement field with respect to time, multiplied by the mass density rho. So when you're describing the dynamic problem, there are additional coefficients you have to define. If you talk about 1D problem, in static, it's enough to define, besides geometry, the cross-section direction of the bar and the length. The mechanical property are just Young's modulus. Now, if you go to dynamics, you also have to define at least the density to talk about that. And then next to these boundary conditions, in other words, impose displacement and impose traction for the Dirichlet and Neumann boundary, respectively. You also have now to define the initial condition for your body. That is at the moment t equal to 0 when you start following the motion. You have to define what is the initial displacement u0 of x and what is the initial velocity v0 of x. And so then I can solve this so-called initial dash boundary problem. Initial because you're talking about imposing initial displacements for t equals to 0. And boundary because we're talking about imposing the boundary displacements or attractions for a particular value of x that is sitting on the boundary. In the finite element setting, instead of starting from the strong form, which is given here, which is a partial differential equation here of the second order, behind derivative of sigma with respect to x, given that sigma is equal to c times du dx, it's hiding second derivative in x. So here you have this so-called hyperbolic partial differential equation with a typical propagation that could be so-called characteristic, and you have a straight propagation. And for some cases, simple cases, typically of bar, you have a exact solution with a wave propagation type of thing. But if the thing gets more complicated, if you go into plasticity damage and stuff like that, then computing this analytical solution is next to impossible. So we still have to resort to using the numerical methods like the finite element method. So just like in non-stationary heat transfer, the dynamics with finite element will give you only partial solution to the problem, and we reduce this set of a partial differential equation into a set of ordinary differential equation. So the starting point, just like in static, would be the weak form of the equation of motion. So this part you can recognize. This is basically we form the equilibrium equation, which amounts to saying the stress, which is a product between Young's modulus and the infinitesimal strain du dx, is multiplied by the virtual deformation, which is the derivative of the virtual displacement dw with respect to x. And here we have work of the external forces, distributed force, well, here it's called F, it could be B. Up to now we call it tangent traction, which is applied in the Neumann boundary T bar. And with the equation of motion, I have a supplementary term, which is basically giving me the inertial force, which is the product between the, let's say, mass, so here the density times the acceleration, and basically the corresponding virtual displacement. So the only difference from the static case is the presence of this term. So I don't have to repeat what we have done for a static part. We have done that in the very first lecture. So I just take into account what we done for dynamics. Namely, first of all, when you do the principal virtual work, this is done in the spirit of D'Alembert. What D'Alembert said, if you have equation of motion which defend both in x and t, you can imagine taking a photograph. So you froze the instant in time, and then you turn this dynamic motion problem into a problem of static equilibrium, where this term, which is inertial force, mass times acceleration, is taken on the other side and add artificially to a set of the external forces. And then basically you can apply the principle of virtual work. That means at the frozen value of time, you are imposing the infinitesimal kinematically admissible displacement field, which is then testing equilibrium by saying the work of internal forces, that is the stresses, and the work of external forces, including inertial effect, have to match each other. So W, because of that, is just function of x, because t is frozen, whereas displacement field, which is function of x and t, is done in this spirit, which means that we are really imposing a solution which would imply the separation of variables. That means only certain waves are admissible in the stuff that we are trying to compute, where the dependence on space and time could be separate. And so basically, the shape functions that are representing the virtual displacement, WHOX, and real displacement, UHOX and T, are the same in the spirit of Galerkin method. We keep the same type of interpolation. So if I go through this development without repeating all the steps, because we have done that already, I will require the derivatives of this to get the corresponding strain approximation. And basically, I'll end up with saying that the given nodal values of the displacement, virtual displacement of three nodes, which are arbitrary, I will obtain a set of these ordinary differential equation in time, where the nodal displacement d of t, second derivative, this is acceleration, is multiplied by a matrix. And on top of that, you have a stiffness matrix times the value of displacement equal to equivalent nodal load, f of t, which quantifies the work of the external forces in terms of the chosen virtual displacement. So this set of ordinary equations could nicely be solved, because basically given the initial displacement, initial velocity, I take my interpolations and I can obtain the corresponding nodal values of initial displacement, called here d0, and of the nodal velocities, called here v0, and I can compute this solution by solving the set of nonlinear ordinary differential equation. So to complete this set of equation, the only new matrix that I have to understand how to build is this matrix M. This is so-called mass matrix. It comes from this term here, where obviously you need the shape functions and you need the density, and you have to integrate over the whole body. So integration of the whole body, given that it's done by the finite element method, is split into an integration of independently over each and every element, and you build your mass matrix for particular element ME. So components of these matrices ME, I write it here as a component AB, is simply NA times rho times NB. And basically, if you have a more than 1 degree of freedom, you would have to have this interpolation for each and every component. I guess the reason why I stick this canonical delta here. Otherwise, if it's only problem, you just have one component, and this is NA and B, and so on and so forth. So if I have two-node truss bar element, recall for computing stiffness matrix, internal forces and stuff like that, it's typically enough to have one Gauss point. Obviously, if I have a mass matrix, given that these functions for two-node truss bar element are linear polynomial, so linear times linear builds me a quadratic polynomial. And we could see that one-point integration for Gauss can only integrate exactly linear polynomial. So you have to upgrade, you have to go to two-point integration to get mass correctly. If you do that, or you can integrate it directly, it's not that complicated. You get your mass matrix to be a consistent form, which is equal to rho, the density times the length L of a particular element divided by 6. And then here you have form 2, 1, 1, 2. If you have cross-section A, which is not equal to 1, then of course you would have also here everything multiplied by A, so the A rho LE. There's interest, if you talk about the explicit method, to use an approximation for such a mass matrix. And this approximation is done in many different ways. There's in the book of Zinkiewicz-Taylor, one of those early versions of finite element method book, they have discussed 2 or 3 different versions of diagonalizing this. But here the simple one is just physical. If you want to compute the diagonal mass, you simply move all these coefficients to the main diagonal. So 1 goes here, so 2 and 1 it becomes 3. 1 goes there, 2 and 1 becomes 3. So 6 divided by 3 becomes 2. And you can obviously see that diagonalizing this matrix and keeping the full mass the same will be simply rho L divided by 2 and then times identity matrix. So this will be certainly the simplest type of matrix you can imagine. And basically the idea is that it's kind of intuitively clear that this is fine, because again, if I had a cross-section A, this will be A rho LE divided by 2. So the total mass of the bar of the mass density rho and the cross-section A and the length L is equal to a product A rho times L. And then you take half of this mass, you put it to one node, and you take a second half, you put it in the other node, and you have your mass matrix represented kind of in a crude way approximation. And that is kind of a diagonal part, which when you do assembly, of course, assembly of diagonal matrices again will be a diagonal matrix. So we'll see that in a second. For the explicit schemes, of course, this is a big advantage because it drastically reduces the cost of computation to only n operation for the n equations, as opposed to implicit method where the cost of computation is n to the power 3. On the other hand, you still have this problem of a conditional stability, namely the time step could be limited only to a particular length of the say interval, and so you should not be going kind of too ambitiously with that. So you could always balance between explicit and implicit scheme with the fact that you have more operation per step, but you have many more steps. So in rough estimate is explicit scheme. If you want to use them, should be really used for some very short duration type of computation, something like explosion, impacts, and stuff like that. Whereas implicit scheme, if you can afford, you better use it in any other type of situation. Now, what I was presenting here, a set of these equations, is something called a non-damped vibration. There's no damping phenomena. And if you study quantum dynamics without dwelling too much on material behavior, your typical exposure to that would come to say, but in reality, we have a damping, and you have to have some kind of exponential decay of the vibration amplitude. When you do these experiments, the vibration starts and after some time stops. And if you monitor the amplitude of vibration, you can see that kind of reducing down exponentially. So the one model which fits nicely into this type of solution is viscous damping, where you say that the damping phenomena are represented by a damping matrix C, and then the proportional to a velocity that is d dot of t. Now, physical justification of that is kind of a little bit shady. That would mean that your structure is sitting in the, let's say, a barrel of oil, and then oil being a viscous type of liquid, and when you're vibrating, you have a resistance of oil doesn't want to move viscously, and then you have this type of physical justification for damping. But that's not necessarily the reason why they introduced it, because not many structures sitting in the oil. It's just simply because experimental observation of this is this exponential decay, so it happens that fits nicely. Then the second simplification in this case, which was introduced, was saying that this damping is a so-called Rayleigh format, where the damping matrix is a linear combination of mass matrix and stiffness matrix, with A and B being chosen parameters. So this linear combination of mass and stiffness matrix is chosen because it then allows us to keep the pre-vibration modes, because if you start solving this problem, you can go similar to this, what I was doing here in heat transfer, when I was arguing that when you go from one equation to a set of equations, you can actually do this, the eigenvalue solution here. So you can do the same eigenvalue problem solution for the dynamics. But this time around, given that this is second derivative, you'll have, instead of lambda, you'll have something like omega squared, and then it could be exponential of I omega, which could cosine omega t plus whatever I sine omega t. So both the modes will be different, and the values of these things will be different. So this is your model superposition analysis. If you did a simple course on dynamics or linear dynamics, I'm sure you have been through this already. So the advantage of this choice of Rayleigh damping is that allows us to keep the eigenvalue, eigenmodes, or let's say mode shapes of the vibration that you have computed from a non-damp case and to remain the same in the damp case. However, the physical justification of such a model is certainly not very sound, because basically, as I said, if you want to justify that the damping matrix is a coefficient A times the mass matrix and the coefficient B times the stiffness matrix, that would imply that basically in your equations of motion, you're adding this extra term that not only have inertia effect equal to forces that are mass times acceleration equal to the forces, so better than Newton, you're adding this type of barrel type of resistance, which is A rho times du dt. It's like some kind of a damping term from the outside. And then also you're saying inside that the behavior of material is not just simple linear elasticity, but sigma is equal to E times du dx, but it's actually proportional also to coefficient B times the velocity, that is the derivative or rate of the definition, that is derivative, second derivative of u with respect to x to give you a strain, then again with respect to time to give you the rate. So we actually studied this as the first internal variable model. We call this linear viscoelasticity, and we saw that although it is the simplest one to give you the interpretation of what is called internal variable and how to get the evolution equation and so on, in reality it does not really represent much real physical behavior of material. But people use it, and they typically identify this two coefficients A and B by matching the required so-called damping ratio, something like a steel taken 2%, concrete 5%, or something like that, to a given range of frequencies. So you can only match these two values. If you do better, then you really have to go into explanation that I really covered once shortly. So I can actually, certainly we have done that in a sense that was already discussed. So let's say I now want to study how to solve the set of second order differential equation in time, where I have mass times acceleration plus damping matrix times the nodal velocity plus the stiffness matrix times the displacement, all dependent on time, equal to the equivalent external forces F of t. And I have my two initial conditions, which are initial displacement d0, initial velocity v0. So the solution will be solved again with the time integration scheme. And I start by presenting this Newmark scheme. Newmark was a professor of engineering at Urbana-Champaign with, let's say, very engineering methods. And he devised this equation simply by, let's say, engineering intuition. It turned out this is one of the, let's say, the most fertile equations that have remained, that remained in use of the mathematics community even to the present time. In fact, the Newmark scheme is not a scheme, it's a family of scheme, which has these two free parameters called beta and gamma. So what he has done is basically said, okay, if I have some kind of approximation of the acceleration, he has done with the 1 minus gamma times an, the acceleration time tn, and then acceleration n plus 1. First of all, to really recall what we are doing is one-step scheme, and we start the computation by given values of nodal displacement, velocities, and acceleration, and time tn. They would recover all these values at time tn plus 1 such the equations are verified. So we need sufficient number of equations next to the equations of motion and time tn plus 1, which are written here. You need two extra equations. So I was saying that the Newmark divides them by saying a sort of what will be variation of the acceleration typical time step. And then he is then averaging this sort of acceleration with the parameter gamma. So you can compute your velocity at a plus 1 as Vn plus h times 1 minus gamma an plus gamma an plus 1. And then you take another integration. So you can obtain that your displacement Vn plus 1 is equal to n plus hvn plus h squared over 2, 1 minus 2 beta n plus 2 beta n plus 1. So it's up to you to choose these parameters beta and gamma. But typical solution, of course, in the spirit of choosing beta and gamma, you can have a couple of different formats how you actually compute these equations. So first, what I call format A, you recall this alpha ski for heat transfer also have two different formats. Either compute V or compute D. That's similar here. Either compute A or compute D. So basically, first of all, when you start the initial computation time equal to 0, where you only know the initial displacement, initial velocity, you have to enforce the validity of this equation of motion and time t equal to 0. And that would imply you have to compute corresponding initial acceleration in agreement with the imposed displacement and velocity time t equal to 0 by enforcing that ma0 is equal to f minus cv0 minus kd0. So once you have this a0, you have this situation where all the values are known at time t equal to 0, and then you go step-by-step computation of this kind. So in A format, you first do predictor by using the known values. That means that you have dn plus 1 tilde as dn plus hvn plus h squared over 2, 1 minus 2 beta an. And you have vn plus 1 tilde equal to vn plus 1 minus gamma h an. Then you plug these known values into the right-hand side, and that becomes your effective load vector, influenced with the damping times this vn tilde, and stiffness times dn plus 1 tilde. And here you keep only the values that you had in the full approximation. So this will be m plus gamma hc and plus beta h squared k. So this gives you unknown, which is the nodal value of the acceleration vector at time n plus 1. And this is now a set of algebraic equation, in particular here is linear equation. So you appeal to what we learned already, a Gauss elimination method, where you kind of triangularize your effective stiffness matrix. Effective because it's not only stiffness, but it's contribution for damping and mass. Then you do forward reduction, back substitution. You obtain your an plus 1. And then you simply complete this update on top of dn plus 1 tilde, vn plus 1 tilde. You add beta h square an plus 1 for the first dn plus 1, and then gamma h times an plus 1 for the vn plus 1. And then you're done with the solution. You have everything at time dn plus 1. And then you can also do it in format D. So to start with, initialization is the same. Given initial displacement, initial velocity, you compute corresponding initial acceleration, a0 such that ma0 is equal to f minus cv0 minus kd0. And basically for each step, now you predict the intermediate value of the velocity and acceleration. That we call this, there's a tilde forgotten here. So v plus 1 tilde is equal to, you can work it out from these two equations to express what v and a depends on the given these things. So basically that vn plus 1 tilde becomes beta minus gamma divided by beta vn plus beta minus 0.5 gamma divided by beta times h and all multiplied by an. And an plus 1 tilde is equal to minus 1 over beta hvn minus 0.5 minus beta divided by beta an. And then again, you have this effective load vector, which is the true load vector minus mass times this predicted acceleration minus damping times predicted velocity. And here you organize your effective stiffness matrix with contribution of stiffness, damping, and mass. And this time around, you're computing incremental displacement. So this incremental displacement should be un plus 1. All the current became un, sorry about that. You have a dn plus 1 is equal to n plus un plus 1, the one that you just computed. Vn plus 1 becomes this intermediate value, Vn plus 1 tilde plus, again, correction gamma divided by beta times h times un plus 1. And finally, an plus 1 becomes 1 over beta h squared, un plus 1 times this predictability un plus 1 field. So basically, the idea, either A format or B format, you cancel the whole set of the unknowns, and the main cost becomes this solution, the set of algebraic linear equation when you discretize this, and either computing n plus 1 or incremental space n plus 1, this will be the kind of dominating cost. So the game after that is to say, can we judge the stability, consistency, and so on and so forth? You can rely fully on the analysis done in the heat transfer case, and I'm going to go into detail that basically what we do, we kind of diagnose the system. We turn this whole system text to Rayleigh damping into this is your model equation that you separate this dependency, so you can turn this to n independent vibration modes, where these are so-called model coordinates that are fully uncoupled given this type of damping. So instead of mass, you have 1. This is the way you normalize these eigenvectors, and then instead of the stiffness, you have omega I squared. Your stiffness matrix become omega I squared, the diagonal matrix. And then damping, diagonalizing C, which have contribution from mass and stiffness, you call these coefficients the 2 times psi I times omega I, missing here, sorry about that, times yi dot. So psi I are these damping coefficients that you want to choose. And so it turns out that if you go through the checking stability, you can say that you have unconditional stability for 2 beta larger equal to gamma, and gamma larger than or equal to 1/2. So one of the favorite choices is if you take gamma to be 1/2 and beta equal to 1/4. If you go back to the Dirac equation, if you take gamma equal to 1/2, you're basically taking acceleration to be half of an and half of an plus 1. You're taking really average acceleration method. If you take beta equal to 1/4, again, you take this acceleration to be half of an and half of an plus 1, and you simply integrate. So this is the one choice, and it's already unconditionally stable. But that's not the only choice. You could take, let's say, other choices for beta and gamma. We'll talk about that in a moment. Then the consistency, that's the order of the method. If it turns out if you take gamma equal to 1/2, the numeric scheme is second order method. In fact, it's actually rather easy to see that. If I want to exploit what we've done in detail in taking the first order system, I can take a single second order system, this equation md dot plus cd plus kd equal to f, and I can turn this into a 2 times as many equation of the first order by saying that I split this so-called state space approach. Instead of d, I take a d and d dot to be unknown variables, so I'm talking about displacement and velocities. And then first equation will come y dot equal to z or y and t. First equation will take y dot equal to z, it will be simply d dot equal to d dot, it's just as in t. And the second equation will be y, which has already the second component to be d dot, then you dot it again, that become d double dot, that's acceleration, equal to m minus 1. And here you have f minus cd dot minus kd, which is basically your equation of motion written the way where acceleration is fulfilled on the other side. So when I look at formally, this is my first order differential equation. It looks like heat transfer equation. And then I can use a trapezoidal rule so that I can conclude that yn plus 1 is equal to rn plus h over 2, h being the time step, zn plus zn plus 1. So given what is z, that becomes dn plus 1 is equal to dn plus h, vn plus 1, and vn plus 1 is equal to n plus h over 2, an plus n plus 1. So basically, this is really your trapezoidal rule approximation, which we already studied for heat transfer. And we concluded this is a second order scheme, which confirms that. So keeping in my gamma and beta given this way, you can get this implicit, let's say, numeric scheme, which is trapezoidal rule and which is heavily used for this computation. Now, there's nothing to stop me to extend immediately this type of consideration to a nonlinear dynamics as opposed to linear dynamics. I'm considering the case when I have a nonlinear elasticity when the behavior happen to be defined in terms of the strain energy potential W, such that the hyperelastic behavior would allow me to say the stresses are computed as a partial derivative of this potential with respect to the strain. And I can define my tangent modulus as a second derivative with respect to strain to complete this picture. So then my equation of motion in the weak form would be the ones that I had in the strong form. That is typically the virtual strain dW dx times the stress sigma computed as a first derivative of my potential minus the virtual work of the external forces, that is B times W integrated omega, and the traction T applied at the Neumann boundary times the corresponding virtual displacement W. And on top of that one, now in dynamics, I have to include my inertia effects that we get rho times the second derivative of displacement with respect to time, this acceleration, and multiply by the virtual displacement. So then when I'm doing my finite element approximation, what I do, I still have inertial term, which is linear. It's just mass times acceleration. The fact that I have nonlinear constitutive behavior, like nonlinear elasticity, does not change this effect. You know, don't care what is behavior of material. If I take it in the inertial field, this is the inertial force. It's just proportional to the mass. And that the only complexity constant, you have internal force to be a nonlinear function. In that respect, you know, when you go with the implicit scheme, you cannot reduce to a single equation like we're doing here in the D format or here in the A format, because now the internal force will be something that is nonlinear. And so this equation particularly requires a certain number of iterations. And that becomes a little bit of a hassle, which you might want to avoid if that is possible. And this could be done by the explicit scheme, which we'll discuss in a moment. So again, the mass matrix is the same, internal force was computed again the same, and so on and so forth. Basically, the idea is that if you have two node trust bar element, this is computed with a single Gauss point, and these two have to be two Gauss points, and so on and so forth. So basically, when I'm computing this, if I want to make it more efficient for the case of, let's say, nonlinear elasticity, I can also look into the explicit method, which makes these things a little bit more efficient. And basically, the idea is that you can still keep a second order approximation, but make it much more efficient as a central difference scheme. The development I took is from the book, which was at that time kind of the book. Dahlquist was a very good numerical analyst who taught many of these guys. Some of them went to US and kind of spread his teaching there with the book that he wrote. Typically, that touched a lot of people, basically. So the idea goes as follows. If I want to have computation, the time integration scheme with the steps from T1, Tn, Tn plus 1 all the way to uppercase T, I know the values at the time Tn, I know the time step, and I want to compute the, let's say this equation of motion, nonlinear case, mass times acceleration n plus 1, plus internal forces, a function of Dn plus 1 equal to the external forces. I want to do this with the explicit scheme. So what is the explicit scheme? First of all, I take a approximation of this first equation, d dot equal to v. I can take this with the double step that I say that Vn is equal to dn plus 1 minus dn minus 1 divided by 2h. I can do the same type of approximation with the mid step. That is Vn plus 1/2 is equal to 1 over h dn plus 1 minus dn. And Vn minus 1/2 is equal to 1 over h dn minus dn plus 1. So from this comparison of these two results, I can conclude basically that 1/2 Vn plus 1 and Vn minus 1/2 is equal to 1 over h dn plus 1 minus dn. And so basically, if I take that Vn is the average of Vn plus 1/2 and Vn minus 1/2 divided by 2, I can obtain that Vn plus 1 is equal to dn times h Vn plus 1/2. If I do a similar approximation to V dot equal to A, I can take the Vn plus 1/2 minus Vn minus 1/2 divided by h is equal to An. And then basically I can connect these two things together. So when all is said and done, I can say that Vn plus 1/2 is equal to Vn plus h over 8, h over 2 times An, and dn plus 1 is dn plus h Vn plus h over An. And again, if I shift n to n plus 1, I get Vn plus 3/2 is equal to Vn plus 1/2 times plus h times En, and then that gives me that Vn plus 1 combination of these two results gives me Vn plus 1 is equal to Vn HO2, AN plus 1. So it's a kind of long development, but the guy knew what he wanted to obtain at the end. And so we have a second order approximation with something called explicit method, where basically you say that dn+1 is dn plus hvn plus h squared divided by 2 times an is the first equation you solve. This is the predictor. You notice here that this is fully explicit computation. And if you have n equation, or call it whatever, m equation or p equation, whatever, 1,000 equation, you will have just like 1,000 components here and there, and you have to sum up 3 of these vectors which has 1,000 components. And basically you get your operation of the order of magnitude of the number equation. Now, this is the most demanding step. When you solve it with the Gauss method, if you have 1,000 equations, this is of the order n to the power 3. When you have this factorization, so there will be like 10 to the power 9. If you take 1,000 equations, it's like 1 billion operations. However, if you now take the mass to be a diagonal matrix of each and every element by lumping mass, we have a rho times A times L divided by 2, and then diagonal matrix 1, 1 on the main diagonal. You sum it up, you assemble. Again, you're going to have a diagonal matrix. So solving this set of equations is very easy with the m being diagonal. It's simply the residual, that's the external load minus internal load for the given dn+1. So see here you have dn+1, so you simply evaluate the stress and the behavior. You don't have to iterate. There is no, what you call it, obligation to go through this elaborate computation because the value is already given. And then you simply divide the value of residual with the corresponding component of the mass matrix, and you get your acceleration. So again, costs you n operation. If you have 1,000 equations, it costs you 1,000 operations. And then finally, once you have this an+1, you can then update. And again, with 1,000 operation, you get Vn+1 to be Vn plus HO2, an plus an+1. So the big advantage of explicit scheme also gives you a second order approximation, like a trapezoidal rule. And the advantage is that cost of the computation is much smaller. But here, basically, you can show that this is a gamma equal 1/2, but beta equal to 0. And so, because if you go back to what was the original type of approximation of this one here, so taking a beta equal to 0, this will kick out. So you have dn+1 equal to dn plus hvn plus h squared over 2 multiplied by n. That's precisely what we used. And then gamma equal to 1/2. That was second equation. That was the last equation. So the central difference scheme is beta equals 0 and gamma equal 1/2. Both of them. And then trapezoidal rule is beta equal to 1/4 and gamma equal 1/2. So this first choice is explicit. The second order approximation, the other one is implicit. It's again a second order approximation. So these are really type of 2 integration schemes that have been heavily used in different applications. I can show you one or the other. Now, this explicit scheme of central difference was heavily used for the wave propagation problem in the case of impact explosion and stuff like that. It turns out that, of course, it's only conditionally stable, and the critical time step is limited. You can express it in many different ways. For example, here in terms of wave propagation speed, basically this is like Cmax. If you have consistent mass, you have analysis in the paper by Odin Frost. The time step is limited to the length of the element divided by square root of 6 times this propagation of the waves, which is a tangent modulus divided by rho square root of that. It turns out if you have diagonal mass, it's actually a larger critical step because square root of 6 is larger than 2. It would be square root of 4 would come down to 2. So basically, it's funny, you do kind of more close approximation, you improve the behavior of your method. But anyway, that's how it works. So the idea here that also there was a why do I carry this again? So basically, this is the computation I have implicit scheme. So I have my approximation that averaging the velocity, averaging acceleration to get corresponding advancement of displacement, the velocity. Then I can obtain what is velocity n plus 1 with respect to Vn, acceleration n plus 1 with respect to An. And then basically I can set my set of equation for nonlinear elasticity if I need implicit scheme this way, that I have to iterate with internal force being nonlinear function of displacement. In particular, I'm computing my incremental displacement. So at every iteration, I'm updating the displacement, I'm updating velocity, and I'm updating the acceleration. So the main cost is really solving this set of equation every time. If I want to get Newton, I have to have this tangent stiffness and so on and so forth. The experience that I had is really, in my thesis, I studied the part with the frictional contact. We have a non-associated type of plasticity and stuff with the structure that can slide on the support and things like that to reduce the effects of maximum dynamic loads. And when I studied dynamic contact, it was always easier to deal with that. And then I realized, okay, before you start dynamics, you actually have the history, you have to take into account the statics. So I suppressed the inertial effects, and I had much more trouble converging in my stuff when I did not take into account dynamics. So typically, if you really had problems trying to obtain the solution, many people are artificially adding this dynamics because dynamics are kind of making things more regular, more smooth. And then you can compute these things in a better way. I talked to many colleagues who did research work before me, so they didn't have this powerful method in computers. They were studying like instability of shells by pretending there's like going in dynamics and many other things. But at the end, maybe it's not so wrong because if you have this geometric instability with large production displacement, the things after that goes very quickly. If it goes so quickly that you can have a sound, typically a boom, and then in French it's called claquement, somebody hits you, slaps you in the face, this is clack, and the thing like that. So basically mixing dynamics and nonlinear problems, often it can help. Unless you're really unlucky, you go into something called chaos. When you go into instabilities, then you really have a problem describing the whole behavior. But if this behavior is relatively stable, but just nonlinear dynamic helps. If you're unstable, dynamic is a hell, it's called chaos. And so you don't really touch that unless you know what you're doing. So basically, if you really want to get proof of stability, there's one thing that you can handle is basically you go back to the original problem. And if the original problem doesn't have any damping, I just have a mass times acceleration plus the stiffness times the displacement. I multiply this by the velocity. So I have a scalar here. And it so happens that this is nothing but the time derivative of my kinetic energy, which is 1/2 velocity times mass times velocity. And this is nothing but the time derivative of my internal energy, which is 1/2 displacement times stiffness times displacement for the linear case. And so I recover that you have something called Hamiltonian. This is total energy, kinetic energy plus potential energy. And sum of these two always is conserved. If you have no external load, you just start from the initial vibration. So, the relation is described by functions of cosine and sine. So this becomes something like sine squared, this becomes something like cosine squared, or the other way around, depends on the particular position. And then sine squared and cosine squared always build up to the same thing equal to 1. And actually, you can show that in linear elasticity, these trapezoidal rule preserves the energy. And that's another way of you can show the unconditional stability. Now, if you have a nonlinear problem, you need to have certain restrictions. And it's not so easy, and it becomes much more tricky to be able to study stability of these type of schemes. And this was heavily researched early on with the works of Belichko, Hughes, and stuff like that, with the books coming from this type of thing. So this is the kind of thing that I wanted to. But if I go back and I say first, let me illustrate this idea. If you didn't like the type of simplified idea of damping, which is this guy here, I can do a better job, and that's what we are doing. Let me do that here. This guy. What the hell is the other guy? So share screen again up. This I think we are. Where's the stuff here? Maybe. Hopefully you see the screen. Is it fine? There was like if you wanted to get a better grasp on behavior in earthquake, And also the better interpretation of these results when you have a local damage with like hysteresis loops of these stresses, you really cannot say that really can represent this very seriously. And then if you really want to take into account damping, if you have a complicated situation of this kind, you have a sources of damping coming from everywhere. Basically, you have here that the wave propagates in the support in the soil, and then you have a damage of a particular structure with little cracks, big cracks, and sliding, and so on and so forth. So, giving the physical justification of damping is certainly not enough to take really. So basically, here was I skip that because this repeats the same story that you just heard, and basically saying that really is not good enough and you need something better. So I go here and say how you get this better. Here, better would be that instead of really, simply say damping matrix alpha and it was beta k. You need a response which takes into account like at least 3 different phases of a response to earthquake that is like a very, let's say, mild shaking. When you have this earthquake which are not so severe, then you have a strong shaking that go into some kind of damage. And then finally you have a free vibration of the structure which has been damaged. And then you have to be able to represent that. So obviously if you do Rayleigh, you cannot check all this because you can only fix 2 frequencies and get the corresponding damping coefficient and basically not worthy of repeating if you had this in linear analysis because you're not going to do it here, that's for sure. So what we've done is the stuff that I presented already for couple damage plasticity model. First, what was PFGL, and we put it forward. Then you have both plasticity and damage, and you can get this complicated behavior that you can have both change of the elastic response, and you can have a, let's say, residual deformation. So first job was doing with Damian, and doing this computation on both sides. I presented this stuff. And then second work was doing this upside down, that you have like a stress-based interpolation. And we had to line up like kind of 8 different internal variables for 1D problem, which is multiplied by model of a beam. And you can get this kind of stuff. So basically, that was also complemented with the hybrid stress type of formulation of our problem, so that you can have a very robust computation with the linear hardening and softening. We were able to cover the typical area of the hysteresis loop. That means you have the same energy dissipation for each cycle, but it is just linear hardening or softening. So that means that you can have a single iteration to get the right result, and that you can able really to get quite a good results for this type of damping phenomena. And basically, this was one thing that I wanted to show. Basically, then this gives the argument how you can do with the implicit method. Of course, you have to iterate and so on and so forth. And I also want to show you what and how you can do with implicit method. Sorry, with explicit method, my mistake. And basically, this is the type of case that we studied after the World Trade Center attack. Sometime later, we were hired by the French military division of this nuclear institute guys, and wanted to check what happens if the big airplanes would crash into the structure they try to protect. Not only nuclear power plants, but kind of storage of nuclear materials, basically the arms and the nuclear bombs which are sitting there. They wanted to see what happens, if you have a bomb hiding behind some kind of shelter, and you have an airplane hitting into that. It could have done much bigger damage than simply hitting some kind of World Trade Center. You kind of remove bunkers. Many people will argue it will become a better place, but it is just a joke. Should not record this, my God. So the idea is like here we have illustration. There was a previous computation what happens to a plane crashing into these nuclear power plants. And then basically is your typical scheme. You have a plane that is crashing there. You have a point of impact, either projectile or plane. This is what is called ensemble reactor. This is this heavy shell structure, which is protection from reactor explosion. Reactor itself is sitting there and the foundation and so on and so forth. So basically the idea is that if you want to study this, what was available before is given here. they first had a very simple model. This is the best one, the most often cited was this Riera model. So the argument goes as follows. You cannot imagine the most simple argument. Basically, that the whole plane was considered like a bar. And then the plane flying, you would compute the kinetic energy of the bar, which is 1/2 times the velocity times mass times velocity, or mass times velocity squared. And then basically the plane would hit the obstacle. It could be this the protection structure of nuclear power plant, and the other structure trying to protect. And then without modeling what happens with the obstacle, you would assume that the plane is a elastoplastic bar. So by hitting the obstacle, the elastoplastic bar would plastify. You have dissipation. And then you take a kinetic energy minus the dissipation, you have the remaining energy which has to be taken by this obstacle, and you spread it over a certain time, and then you have this kind of response spectrum analysis stuff that how you can design and how this could be handled. And this was done for typical small planes that people are using if they have enough money, this Cessna Learjet and so on and so forth, eventually a military plane. And what's common to all these planes, they're much smaller than the commercial planes that are falling down eventually. So basically, luckily, not many of them fall down. So at that time, nobody considered this seriously because the possibility of the impact of this kind was 10 to the minus 7. Roughly, if I want to simplify, it would be that 10 to the 7 would be like 10 million planes going down, only one would hit the structure. And so making such a crude model, okay, it would be probably acceptable. But then, we said, but this is really not the way, because your airplane is not a truss bar, it doesn't really deform this way. So we worked on two sides. We worked on improving the model of this airplane, going into large elastoplastic deformation, just the one that I was presenting yesterday, and then doing impact and contact and frictional contact. Again, I commented on that very quickly yesterday, but still we did it. And then basically you have this way only define what is the loading that goes into a structure. And then you really have to take a serious model of your structure to be able to see if the structure is going to be penetrated, which is the stuff that you're trying to prevent, or it will be just damage and the thing like that without any penetration. So you really have the protection role of your structure ensured. So basically, first with the modeling of the airplane, because completely smashed, you have very large displacement, large rotation, and we worked a lot on the modeling of the shells with the models that were able to do this very large rotation in a single shot, so you can kind of squish the plane and handle this in a very nice way without any problem. And then we were also working on large deformation elastoplasticity with several different theories in this domain, Paddy Gazdin, Lotfi Sharfi, and so on. So basically, that we were able to get this large elastic, large plastic deformation of the plane which is hitting the very stiff obstacle with the necking phenomena and so on and so forth. In fact, all this at the time we were working on that was motivated by a car manufacturing type of thing, with collaboration we had, something called sheet metal forming. Once you produce these thin sheets by a lamination process, then you go and you first try to put the desired form of the car body, so it becomes for sports car very nice, so people buy it and pay more money just because it looks nice. So this is kind of the same problem. The only difference here is not to sell this plane, but to understand what exactly is the loading that it's putting into the structure when you hit it and when you have a frictional contact and so on and so forth. So the second point, we had to have like a impact, and then the force that is transmitted in time has to be handled with a high precision. So the choice of the time integration scheme was not without any importance. So on top of the usual schemes, which are trapezoidal rule or central difference scheme, we can also look into the schemes that are doing a physical type of properties of the problem. There's something called energy conserving scheme, which ensures that energy conserves your free vibration or energy dissipating scheme, which ensure that high frequencies are dissipated because you cannot handle this correctly. When you have very coarse mesh, the high frequencies become kind of gibberish. So the best thing is to try to eliminate. So we tested this in this Bosch's thing. This is multi-body system dynamics. We'll talk about that a little bit tomorrow, day after tomorrow. But the idea is like that this is the thing that it was like a swing. So we have these hinges here. So it's a structure which is unstable, which can swing left to right. So these two bars, these two links are very stiff, and this one is rather flexible. And here's a mass in the middle. So then you hit this mass with a triangular pulse that is given until 0.36 or something like that. And then you let this swing start going to the right. So these are successive deformed configuration of the swing. And in this configuration, you can say just swinging. And let's say the dominant motion of this is certainly like bending or rigid body motion. And then at a certain point of time, more precisely now 0.64 seconds, this link that want to go up and that link that want to go down, they come in conflict because this flexible link is the one that should be connecting them. They said, stop, I cannot be stretching like crazy. So basically at that point, you have some kind of impulse that is trying to stretch this link. So before that, the swinging was done by the bending. So this is your beam bending. We'll talk about this beam models and stuff like that. And now you kick axial deformation, which is typically much stiffer than the bending for the beam. And so this stirs the like non-smooth displacement. You can see that at that point you start having something like a non-smooth displacement evolution. And now if we use energy conserving scheme, you can see that after the loading stops at 0.3566 is basically you can conserve the energy fully. But with the energy conserving scheme, after this 0.64 second event happens, you basically have something which is really entering there into the, let's say, axial deformation, and your stress computation becomes quite meaningless because I think we put only 8 elements. So representing high vibration modes with 8 elements, you need something like 10 elements to represent a typical wave. It was almost impossible. So basically you have some kind of the high frequency vibration which never really settles down. So deciding if you have plasticity or not on the basis of such computational stress is not meaningful. But if you're now energy decaying scheme, you simply take out these things and then basically you can carry on the smooth. You can see that the energy that you take away is not that big. High vibration modes are not that important. You still have this energy decaying and then improve the result on your stresses. So this also was tested to get the proper type of interpretation. And then we want to run this with the central difference scheme because basically this is very short duration type of impact. The airplane hits, slides a little bit, and poof, that's over. You measure this in seconds. So basically, with the central difference scheme, you have this your dn plus 1 equal to dn plus delta t times vn plus delta t squared. There's 1/2 missing here times an. Then mass times acceleration equal to this is now the structure that is experienced. This is like a frictional contact that the plane is doing on your structure, minus the internal forces that you are computing the structure because it's the plastic line damaging and so on and so forth. And then velocity is completed with the n plus 1/2 times delta t and added on top of Vn. So the structure was this heavy concrete and structure with the reinforcement and stuff like that. So what we are doing is you take into account that the damage model could be first Masdar that is giving us a tropic. Then you have this discontinuity to go into the localization, the one that I was presenting the end of the last week. Then you can put on top of it plasticity, have couple damage plasticity. And basically in the plasticity, you can take into account hardening, but here it's kind of funny because since you have impact, normally this hardening goes in the other way, but here it's like it goes stiffer and stiffer because you're compacting the concrete with impact. And then once you reach a certain threshold, you simply pulverize the element and you kind of make it disappear. Now, in a explicit scheme, it's not a problem to make element disappear. It's not going to perturb your computation. You can simply remove it and then carry on with your computation. So that allowed us to have a very complicated model, but rather simple computation because we did not have to worry about convergence. So contrary to this damping phenomenon we're doing in this implicit computation, we took linear hardening, linear softening. Here you can make it as nonlinear as you want, because with the explicit scheme, you always give the displacement, and you know that it's defined the best value of displacement in the explicit computation. And so all the rest is just evolution equation of these internal variables that could be made to converge without any problem. And basically you have a behavior of your structure. So this way, when we are running this and showing it to these guys, they're saying all the time. So you can have two cases. Either you have like a case where the slab is penetrated, a case where the slab is not penetrated, for it's more thick. But when we're running this, there was three of these engineers who followed us. One of them supposedly expert and stuff. So he kept saying, where's the cone? Where's the cone? And basically I said, what the cone you're talking about? He said, well, normally when you look into the penetration of slab, the simplified computation was that you compute your cone, and then you take the shear stress around the cone surface, and you compare this against the force, and you say, okay, is this going to be penetrated or not? Then I asked next time the student to produce the contours of the maximum damage and to run the simulation. So you have it impact here, and then you have the maximum damage it is going all red, going here, and then certain point, poof, you have it this one. So he said, that's exactly what it looks like, because the cone doesn't go all the way to, but you have this part which is coming down. So these guys were very happy with this type of result. But this was what we call hard impact. This is really if you send a projectile to try to see if you're going to manage to penetrate with some kind of protection shell. The situation we had in mind was mostly that these are like some kind of boxes where you store this material, and these boxes are done in a way that the roof is a simply supported slab, because boxes next to each other, if you have internal explosion, you can have this roof lifting off, and then you have a next box a little bit reducing the effect of the explosion in this box, because basically it goes to the roof and not to the adjacent boxes. So basically the second point is that the rear model, which has a airplane which is entering at 90 degrees, which is the worst case scenario, is definitely not easy to reproduce for the structure which is the same side of the airplane. Sorry, none of the planes will be landing on the peak at 90 degrees. Planes are typically landing on some angle. So actually what we had to do is we compute the impacted component with simply supported slab. And basically then you have to take into account the plasticity of the plane, frictional contact and falling apart and stuff like that. So we kept the plane to be elastic and the plane to be completely degrading, and recorded this frictional contact type of thing that you have in the equation of this kind. And then basically on top of that, we had the inelastic behavior of the structure to carry on this computation. Now the trick is this is like a multi-scale problem in not only in space but also in time, because the problem was as follows. When you're computing the frictional contact and the plane crashing into this simply supported slab which is sitting on the roof, you take a very, very fine mesh. And you take, with the fine mesh, you take very tiny time steps to keep conditional stability of a central difference scheme. And then if you want to get results of this computation used in the total structural assembly, if you keep this fine mesh on top of the coarse mesh that is used for the rest of the structure, I mean, if you take such a fine mesh for the rest of the structure, you'll never really get any computation done, especially not to do parametric studies that is optimize the kind of arrangement you want to make so to protect the structure a little bit better. So what we've done is basically we tried to transfer this impact and frictional contact on the fine scale into some kind of equivalent loading on the coarse scale, such that basically the effect for the rest of the structure remains more or less the same. So how these transfers work to get this equivalent loading, what we call here G, you can do it like that. You can do the central difference scheme on the coarse mesh once you transfer the tan Tn, and this is run by this equivalent load G, or you can do the computation on the fine scale where you have this frictional contact there, and then you transfer at the time Tn plus 1. And so what we try to find is the case what is G is such that basically either you do a transfer at time Tn and then run computation of core scale, or you do computation of the fine scale, the transfer Tn plus 1, that you come to the kind of same conclusion. First of all, how do you do the transfer? From the fine mesh, which is here in red, and the coarse mesh, which is here in black. We use this collaboration with my colleague Pierre Villon, who is an expert on the so-called diffuse approximation. This is moving least square approximation instead of the finite element method. So if you want to get the best value of approximated from the fine scale to the coarse scale, you choose a particular point, let's say here the node of the coarse mesh, and then basically you need a certain number of points, remember minimum was 7 or something like that, to take this from the neighborhood, and then you pass a corresponding function that is supposed to be used in approximating this. So this function is something that looks like a coarse scale mesh. Let's here, for example, here, if you take this 8-node solid elements, this is something like a linear function x1, x2, x3, the 3 coordinates of x, y, z, and multiply by the parameters a that you're trying to fit in this projection. So the projection is simply take the result that you're trying to represent in the fine mesh in these different points, and you compare this against the assumed variation on the coarse mesh with the unknown parameters given in this vector A. And then if you want to make smooth from one patch to another, this is in habilitation of Pierre Villon, basically to do document you have to write when you do a thesis, so then he uses it in many different situations. You have this weighting function which can make it like to be compatible and move from one patch to another. And so this is be done with the, minimizing this type of difference between the one and the other. This minimization of this becomes like a set of the linear equation. It gives you these parameters A, and then you get the best approximation of this. So how you use it, basically, you take the displacement computed with the coarse mesh at time n plus 1, or you take projection computed from the fine mesh at time t plus 1. You take let's say the difference in these two, put it in the square. Then you do the same thing for the velocity and acceleration to get the best fit. So this will be one choice of the cost function that you're trying to minimize. And in the process, this computation of the core scale will give you automatically the equivalent load vector in the central difference scheme to be unknown. And then on top of that, we said, okay, what's also important, not only to have a fit of this coarse and fine scale computation, but eventually to preserve the load, in a sense that the load on the fine scale is obtained from the fine mesh frictional contact, and you can get all the work that is done by this, let's say, in this frictional contact type of scenario, and you can compare this against the corresponding the loading of the coarse mesh with this equivalent load, basically, and you match these two. So if you want to impose equivalence of the displacement, velocity, acceleration is one thing. If you want to impose equivalence of the work of the contact force, another thing. And you can also impose both of them by taking Lagrange multiplier approach with minimize J under constraint that you have also this guy. So these are like, let's say, several different methods that we tested. It turns out the best one is one that you impose both the match of the displacement, velocity, and acceleration, and also the contact forces on top of that. Here's the fine mesh up there, and then the coarse mesh down there. So first we did it for the linear elastic problem. We recover these peaks for different projection method. And then we done it for the plastic part of behavior. Then again, with the method 4, getting the closest to the really this transfer from one mesh to another. So basically, in this transfer time, the way it works is the follows. You have your projection of the course from n plus 1, with displacement, velocity, acceleration, and you have your load from the corresponding the contact force. Then you have the computation of the coarse mesh will become like a projection from time n plus 1 of the fine mesh plus delta t projection of velocity at time tn from the coarse mesh to the coarse mesh, and then d delta t is divided by 2 acceleration of the coarse mesh. Then I compute the acceleration, the course motion n plus 1 to be equivalent load g minus f internal computed in the course mesh. And then basically I get my velocity at the course mesh to be at n plus 1 to be the value at the n plus delta t times the projection from an and n plus 1 on the course mesh. And then j would be basically obtained in this manner, comparing these two results. And also you will have a constraint that you want to put on top of it. So this was really like a multi-scale, I would say, both in space and time. And it's really geared towards the feeding into set of different scheme, which is quite suitable for getting this type of thing. So what they wanted to do, the people who are funding us, they said, okay, let's produce some tables and see what structures are safe and stuff. I said, well, better than tables, we can give you this type of, let's say, transformation from one scheme to another. So basically you have this one, which is a fine scheme, and then basically you have an impacted component, and running this basically the complete the structure of your airplane with a structure which is taking the vibration and stuff like that. And then at the same time, you have the behavior of the structure. So you can do it like that. You can have this one and that one running together. So basically, this gives you the local event and then transformation directly to the global event, and you can see how far you are from risk of the complete damage of your structure and things like that. So then you have to devise the strategy of protecting it either by putting some more high walls and stuff like that, and as they go along. Of course, we were very happy with this, and that was the kind of final result that we kind of with taking the scenario of the airplanes landing under some kind of angle and stuff with the size of this airplane. They could do the necessary works to protect further the safety of the structure, and just be happy with the kind of stuff that is computed there. Then we also tried to have this, but unfortunately they already paid too much money for the first part. I said, yes, but if you didn't really have a penetration of the slot, you can still have a problem of this kind. This is a thing that I was already presenting in one of these simulation. Basically, if you have a 3-point bending test, but in dynamics, that starts by putting the load, hitting it from certain height h, and then basically velocity, then you hit the beam is square root of 2 times g times this height h. And so this starts having propagating downwards, comes to the free surface, reflects, becomes tensile wave, and the material which are sensitive to tensile stresses will basically break, and then you can have this part of the structure with something like a scupping phenomenon, spalling of concrete. You can have a part of the structure with this with certain mass and velocity flying off, and you can still hit the stuff it's trying to protect, especially if it's explosives. You can start explosion by basically putting projectile directly into explosion. So if you run this simulation by Dyna 3D, which is done for dynamics, with the finite elements, you cannot really represent what happens to this part of the structure that's falling apart, because basically you only get the damage to be maximum. That means this part is completely destroyed, all is red, and then this means it is eliminated and destroyed. But you don't know how big it is and when it's going to do. So we did this cohesive link type of method, especially with the links being geometrically nonlinear beams that I'm going to be talking about portion mode, you say, next. And the idea is that with these beams, you are able to have correct representation where these cells are flying off. So this the structure was represented by these ordinary cells, and you do this simulation, you can see this cells being connected to each other. That means one block fell off and then flies as the whole mass and stuff like that. So the formation between these different cells is small, but the whole block is now moving as rigid body, and then certainly can damage your structure. So for that reason, these cohesive links have to be geometrically exact Resner beam with the large displacement and the large rotation. So you have this rotation matrix to be cosines and sine rather than kind of linear version of the beam that we'll talk about pretty much next. So this is the stuff that I wanted you to see, and in this particular way. Let me just go back to this one. Okay, PowerPoint, kick out. And basically, what I wanted to show you as well is the kind of thing that that you have to do to have structures that are. Let me just elements technology is like here. Okay. You can have a okay. You can have also the kind of models which are now the models doing transition between the continuum mechanics and structural mechanics models. And so these are the membranes with the drilling rotation. And I also show you how these things are useful to build the corresponding dynamic response of a particular structure. So this is the kind of thing that I wanted to discuss a little bit further. And we can do any other. Let me just do this 1, 2, and then 2 here and there. Okay. So if you want to have, oops, I don't see it anymore. That's not good. Let's go back. So let's go maybe first this one and then do the other one. Okay, up. Share screen. Okay, here. So if you have membrane elements and you want to merge these elements with some kind of structural elements, you do have a problem in a sense that basically membrane elements typically have only displacement that gives you freedom, whereas the structural elements have also rotation that gives you freedom. So the first thing we came across these elements was when you're building a model of a complex structure where the membrane elements and the structural elements are together. So what we're talking when you talk about structural elements, well, these are beams, plates, and shells. We have a kinematic hypothesis on a, let's say, a kinematic type of development of a particular structure. On the other hand, you have let's say, what you call it, something like these folded plates where the membrane and plate action come together. Or here you have like a beam element interacting with the membrane element. So if you're trying to do the computation, you could really be in trouble. Maybe if I give you a small homework, you can appreciate what I'm talking about. Let me try to illustrate this type of thing. So if you have a structure of this kind, and you run this into simulation, here you have a frame. And this has to be a beam element, okay? In particular, I want this to be oil beam element. But then this frame happens to be like really very large, some kind of, typically this on the ground floor, it's a garage, you can put your car, and the upper floor is some kind of wall, which is giving you the stiffness of your structure. So basically, if I take here a beam element, so this is oil beam, I'll talk about that in a moment. It could be like, so typical, you have here 2 displacements for each node, and you have this rotation. And then on top of this one, if I take let's say single element to model this, I just have like a typical membrane Q4 element, which has only 2 displacements. So what could happen basically if I do that? If I apply the forces here, you know, this typical force here would be altogether to F, right? So all the sum of these forces will be F. Then basically if I take this model, the beam will deform in this way, up. And if some of these forces is F, I will have something like this, where this displacement will be equal to F L to the power 3, where L is the length of this beam, and divided by 3 times EI. 3 times EI. E is Young's modulus of the beam, and I is moment of inertia. Typically, you have your cross-section of the beam. If this happens to be like, in the bending plane, if this is your B, the basis, and this is your H, the height of the beam, your moment of inertia would be equal to B times H to the power 3 divided by 12, whatever. So this will be like a stiffness of the beam when you have this one. But in reality, the connection of the beam and this rigid block is so strong that in fact this should not be the correct version. The correct version should be more like something like that. On top of this guy, I have this one. And so this one doesn't deform. So when you move, basically this still moves like a rigid block. And basically the behavior of the beam becomes like that because it remains built into this end. And so it is not really the type of thing that you want to have here. It would be more like a L to the power 3 divided by 12. So this result would be F L to the power 3 divided by 12 EI. So I give you these results and I ask you to maybe check this with your computation or your favorite code. We run the computation here. We take a total force. Let's make it simple. There's no other force but this one, and this is called F. And see what your code is producing here. What is the result that you can obtain in this simple case? Basically, the solution to that is having a membrane elements which have the ring rotation. That means 3rd degrees of freedom that can take into account this rotation and kind of merge those things together and produce a deformation which is more of this kind. Okay, so let me maybe pause here. Let's go on and then up share screen. Good. Nice. So as I said, we want to develop the model which is able to connect both structures and membranes. And basically, this is the work that has been consumed, I would say, let's say, lots of very capable people to get the proper variation formulation thing of this kind to have it done. Maybe I should, let me go back and do this a little bit better. I should first look into what we are talking about when we have a structural mechanic model. So basically, if I take this from a beginning, you can say on top of the continuum mechanics model that we talked about up to now, I can also build my structural mechanics model, where this is typically suitable for the very special shape of your solid body, which has either one-dimensional or two-dimensional, much, let's say, smaller than the other ones. If you have like a two-dimensional much smaller than the other ones, this will be like a cross-section as opposed to length. You would talk about truss bar model, the one that we started studying first, where you only study axial deformation. And then you can also study a bending deformation, and you have so-called a beam bending model. So it's something that is perhaps of interest to many particular application. When I just got to UTC first time, and I was exposed to what was Jean-Louis Bat was doing. Jean-Louis Bat was the retired professor at UTC, who was at the origin of many of these plate models in France, something called the skid kickoff. Many people work on that, but in France it was Jean-Louis Vatos. He was selling his teaching in one of these courses that we shared, that 90% of industrial applications are really structures. So it depends on the domain of industry, but certainly car manufacturing, airplane, and so on. So these are really thin structures, and then using the model like a beam or plates and shells is certainly very interesting. Nowadays, there's a big research called the model reduction, where basically you're trying to reduce the computational cost of a model by using some kind of statistical mode and stuff like that. But if you think of that, using the beams, plates, and shells was the first, let's say, natural intelligence type of approach to using efficient computation, because you can start with a simple model, something like beam, plate, and shell, and then do a more and more sophisticated type of model. So these models could be developed by using kinematic hypothesis, or can be developed directly from Kosterad continuum, which is so-called oriented continuum, because you have a rotation field on top of that. So basically, what is the kind of model this kind? Well, already the very first model we studied is a truss bar element. It could be like this pen that I was showing, the circular cross-section. And then basically you expose this to a gravity field, and taking homogeneity in the cross-section, you can say that the displacement could be described with only a single coordinate u of x, because all the displacement component inside this cross-section, given the loading and the homogeneous type of properties, happen to be the same. So they significantly reduce the computation of the displacement field to a single component, and you turn this into one-dimensional model. So this is only the first hypothesis they can use. But you can also go for the beam model. If I take the same type of a structure and I now apply transverse loading, then the structure will typically bend, change the shape from the rectilinear to some kind of curvilinear because of the bending. And it so happens that I can make a hypothesis how the behavior of the displacement would be in such a case, given that the cross-section is very small. So some of these models that are less usual is something called Timoshenko. But when I was in Switzerland talking from South, I kept talking about Timoshenko, he kept talking about Henke. So at the end I said, what the hell we're talking about? He said, well, this is the case we take into account the shear deformation. So some countries, they call it Henke. In the place where I learned this, they call it Timoshenko, because Timoshenko was professor at Stanford. He was a Russian guy who came to the US and basically developed his books on the elasticity. And among papers, not many that he wrote, was one this on beam with the vibration. You take a shear into account, that they call this Timoshenko beam ever since. So basically the idea is that you have this hypothesis that the structure is such that if you apply the loading, there's no change of thickness. So this is called the thickness of your beam. You keep still the same thickness. And then in the bending, the cross section, which is plane, remains plane again after deformation. And if you take Euler-Bernoulli beam, then you take this cross section to be perpendicular to the neutral axis, the axis being a deformed shape of the structure. And if you don't take Euler-Bernoulli, you take Timoshenko, you don't say this orthogonality is valid. So here's this illustration. So in the initial configuration, this is the part of my structure, it's just a 2D picture. This is so-called neutral axis, typically located in a, let's say, center of gravity of the cross section. It's a fiber that does not extend during the pure bending. That's actually how you define your neutral axis. And then if I want to describe the displacement of any point, which is a distance y initially to my point in the neutral axis, I need this, first of all, I can have an axial deformation, but this will just bring me my truss bar element, so nothing new to learn there. So this time around, I want to have this novelty, which is the case when I have a transverse displacement, which is u2 of x and y. And we say that this is equal to v of x. And so in Euler-Bernoulli beam, I first trace the new position on the neutral axis. So this is this line here. And as v increases, as we go along the beam, along x, this angle here would be dv dx. Typically, you're talking about small angles. You talk about kinematically linear theory to start with. And basically, with the hypothesis that the cross sections are straight, again, this is a straight line. And on top of that, in Euler-Bernoulli beam, it is still perpendicular to the cross section, to neutral axis. Cross section here and the neutral axis are perpendicular, so they remain perpendicular to each other, cross section, neutral axis. So this angle here, dVdx, is also found here. And this will be Euler Bernoulli beam. So I can express the u1 of x and y, displacement, of course, with the corresponding, let's say, rotation, dVdx, times the distance y with the small angles. Of course, with a negative sign, given that this is positive. Now, if I have Timoshenko beam, the situation is somewhat different. Initially, I have a cross-section perpendicular to the neutral axis, and then this new position neutral axis will be parameterized with the displacement field d of x. And then the point, which is initially the distance y from the neutral axis, I have now the cross-section rotated with the independent rotation field, which has nothing to do with dVdx. It's different than dVdx. And then I'm expressing my displacement u1 as a minus theta, because it's small angle, sine theta is the same as theta, times y. So there's really a significant difference here, that here I have a only need for a vertical displacement field, then I have everything. Whereas here, next to the vertical displacement field, I also need a rotation field. So this is your typical structure model, the simplest one they can use to quantify bending. Let's see which beam model is better, Euler beam or Timoshenko beam. Well, depends what you want to do. Here's the form for the Timoshenko beam. As I said, u1 is equal to minus y times theta of x, plus eventually, if I had introduced the horizontal displacement u, then the whole section would be moved by this u, and I would add on top of that plus u of x, u being the horizontal displacement of the point of the neutral axis. But since this would amount only to the truss bar type of situation, I'm ignoring this at the moment, because this will give you a typical contribution for the axial strain. The only component is the udx. And then u2 is given that you don't have a change of the cross section, u2 becomes the same as v of x. In fact, if you want to do refined analysis, the vertical displacement of this guy would be equal to v of x here. Then on top of that, I would add this part here, which is equal to what you call it, cosine of theta times y. But cosine theta being a very small angle is equal to 1, and then minus y from here. So these two cancel, and you get only that vertical displacement equal to v of x. Then, once you introduce this kinematic hypothesis, this is really just generalization of the kinematic hypothesis for truss bar. The rest is just the continuum mechanics. So basically, this is now the way I reduce the degrees of freedom. I have reduced model with the hypothesis this behavior of the strain field is quantified with the Timoshenko beam model. I now apply the usual expression for the continuum mechanics. In other words, I have a strain field which is defined by epsilon 1 as a partial derivative of u1 with respect to x1. So this amounts to saying this is equal to minus y times d theta dx, with this axial deformation ignored, because I said I only look into vertical displacement in this case. Then given that there's no change of thickness, I have a epsilon 2 to be do u2 dx2, but u2 is v of x. So divide the derivative with respect to y is equal to 0. And this is, of course, an agreement that there's no change of thickness, so there's no deformation in this direction. And then finally, for Timoshenko beam, I have a gamma 1, 2, which is 2 times epsilon 1, 2. This is the shear strain. So equal to derivative of u2 with respect to x1 plus derivative of u1 with respect to x2. So that becomes dv of x dx minus the theta of x. And so basically, you have all these strain components to be able to build your strain tensor. Now, you take the simplest constitutive behavior of linear elasticity. In particular, take isotropic, let's say, linear elasticity with Hooke's law, which is characterized by two coefficients. One is Young's modulus, the other one is Poisson's ratio. Poisson's ratio suddenly to get the shear modulus, which is equal to E divided by 2 times 1 plus nu. And so basically, I can say that the axial stress is equal to Young's modulus times the axial strain. So I have the only component of sigma. And then shear stress is equal to shear modulus times the shear strain. I have this one component here. Now, in beam, you want to reduce the, let's say, the computational cost. So at the first step, you just compute these so-called generalized strain measures. So basically, I'm reducing the behavior of the beam, just describing the displacement V in the neutral axis, and the rotation of the cross-section theta. So basically, these are enough to describe the whole behavior of the V. Then I want to reduce also the stress computation by introducing something called stress resultants. Namely, I'm integrating over the cross-section of the beam, so I can have the moment to be equal to the axial stress sigma times the y, the distance to the neutral axis, and get contribution of all these stresses in there. And so given that sigma is equal to E times epsilon 1, epsilon 1 is equal to minus 5 dt dx, I take out dt dx outside with this integral, and also E and so on, and I'm just left with this integral of y squared dA, which is nothing but the moment of inertia of this cross-section. So then I have a constitutive equation, which is of the form on continuum mechanics sigma equal to E times epsilon 1 for the beam written as a moment stress resultant to these sigmas is equal to EI. This is generalized stiffness. This is Young's modulus times the moment of inertia times what we call curvature. Curvature is the change of the theta with respect to x. So for example, you know, for I may be correcting that. Just let me complete this one. So then the shear force is equal to integral of tau dA, and this is the product between mu, the shear modulus, and the cross section times the shear deformation gamma. So I don't need to take these indexes anymore because there's only one line and stuff like that. So just to illustrate what this Timoshenko beam model can do, it's kind of funny. You know, if you have an Euler-Bernoulli beam that you might have studied, you have some kind of a this is your beam in the initial configuration. Then you have these two moments. So this is your Euler-Bernoulli beam. So you have a pure bending mode. Let me put it this way. And basically, what you'll have your axis will bend in this is your v of x, and it will be a quadratic polynomial in x because you actually have to take a curvature as a second order. But if you have a Timoshenko beam, now I have to take it to the thick line, and I impose this to a pure bending mode. You know, I put these two moments here. So what happens in this case is simply this rotates, and that rotates, and that becomes my deformed configuration, this kind of trapezoidal stuff. And so only this rotation count for the variation. So this will be the moment type of thing, and this is your curvature. And if you have a shear force, you know, putting the shearing of this thing, you know, there's you have a shear force on one side, you have shear force on the other side. This is your V. You can say that the shearing will actually produce something like that. And you have dV dx entering there and giving you the shear. So this is the type of strain measures that are typical of this Timoshenko beam. So equilibrium equation could be very easily established in terms of the stress resultants. I take shear force on the left, shear force on the right. On the right, this is V of x plus dx. I developed this in the asymptotic development with the first order terms only kept, and then minus and plus V, they cancel. I only have dV dx plus P being the transverse loading I apply to the beam equal to 0. And then I take a moment equilibrium equation to have m of x and m of x plus dx, and then basically develop again this one in asymptotic development, cancel plus and minus m of x, they should be minus not equal. And then I have the dm dx plus v is equal to 0. So these are two equilibrium equations in strong form. I can turn this into the weak form by pairing the moments with the virtual curvature and shear force with virtual shear strain. Virtual curvature is obtained as a derivative of the virtual rotation, and virtual shear strain is derivative of the virtual transverse displacement minus virtual rotation. So basically, then I can obtain from this one if I need my equilibrium equation, but typically that's the one I'm using for my finite element interpolation. So basically, then I see that the Timoshenko beam model in the weak form has something that is only keeping the first derivative. So it's kind of handy when I'm doing this computation to do that. So let's see which model is better, Timoshenko or Euler beam. And I take for that one a simple test of a cantilever beam. I'm computing the result for what one model and the other model can do when you have let's say a cantilever beam under the end force. So for this case, the moment diagram is linear, starting from 0 here to the maximum value of P times L, and the shear force is constant with P. So basically, if I want to compute directly displacement at this free end, I take a unit force and I pair this in the spirit of the virtual displacement method, and then basically, or virtual force method in this particular case, so I'm pairing the real displacement with this imaginary virtual force and compare this against to the real deformation against the virtual displacement. And so basically from this one, I can obtain that the true result of this one should be PL to the power 3 divided by 3 times EI. This is the bending contribution, and it should be PL divided by mu A. This is the shear type of contribution. So if you have a Timoshenko model, you can reproduce that. But if you have a Euler-Bernoulli beam, basically that one is removing the contribution, the shear. You cannot really reproduce it. So that kind of argues that in many different cases the stuff is better that you do as a Timoshenko model that had Bernoulli one, and then we'll go back and do this in a large deformation setting. But for the moment, so I come back to my elements that I want to make compatible with the Timoshenko beam. So for the moment, we stick with the elements, a membrane, and you want to make it compatible with this Timoshenko beam. As I said, there's a history of really many developments making this, trying to make this work. So first, there's a variation formulation of Rezin and Nagdi that came about roughly the same time. So I never guessed who was the first one. I talked to Rezin, he sent me many papers, and definitely didn't appreciate Nagdi. I had Nagdi as a teacher. I assume he didn't appreciate Rezin, but this is really typical of these theoretical mechanics developments where we were selling his formulation without worrying about how to solve any general problem. So you don't have a judge to see which model and which computational method is capable of solving the biggest number of these different problems. Then one of the few cases when Irons did not manage to find a solution was exactly this, the membrane with the rotation degrees of freedom. And in the book that he managed to write when he left Swansea, UK, and went to Canada, and wrote a book which is very kind of a strange book, not very pedagogical, but with many ideas which are kind of original for this drilling rotation story. He said, okay, forget, stop wasting money. And the non-conventional interpolation were devised along those lines. Allman was doing this, and then the regularization of Rezin formulation was that, and then maybe one of the papers that was during my postdoc, the biggest citation was this robust membrane drilling rotation that we perfection later on with stuff like that. So here's what we call was the Timoshenko beam model. We have a measure of the bending strain, the rotation theta of the cross-section derivative with respect to x, and the shear strains, the derivative of the transverse displacement with respect to x minus theta. Then you have your bending moment to be equal to the bending stiffness, that is Young's modulus times the moment of inertia times this bending deformation. And you have a shear force here, I call it Q, which is equal to the shear stiffness, that is the shear modulus mu multiplied by cross-section A, multiplied by this shear strain. Then you have a strong form of the equilibrium equation, d and dx, derivative moment minus the shear force minus actual distributed plus distributed moment. And in this one, dq dx, derivative of the shear force plus p equal to 0. Previously, I called m uppercase and v for the moment of shear. It's called now little m and lowercase q. I don't know, the changes from one case from another. So basically, the variation formulation, I have my bending stiffness and I have my shear stiffness. And I can start with that. It was a function of both v and theta. So in the beam, I do have a rotation field, and the membrane, I don't. So that is why the variation formulation of Rezin introduced this rotation by appealing to non-conventional formulation of 2D elasticity. So recall we had the equilibrium equation 2D elasticity, divergence of sigma, that is d sigma j divided by dx j, that is partial derivative of the components sigma j respect to j times ei plus fi times ei. This is a distributed load in direction of ei. equal to 0. And then typically we enforce symmetry of stress tensor by already saying that sigma is symmetric. But this time around, if you want to have this rotation field intervening, we abandon the symmetry of stress, and we actually keep this equation that the skew symmetric part of sigma should be equal to 0. In other words, the sigma being non-symmetric, we can now split the stress tensor into symmetric part and skew symmetric part being sigma plus sigma transpose divided by 2, and skew symmetric being sigma minus sigma transpose divided by 2. And then what's conjugate to the symmetric part is the symmetric part of the displacement gradient, and the conjugacy to the skew symmetric part would be the skew symmetric part of the displacement gradient or infinitesimal rotation field. And that's how this rotation field enters into the formulation. So I can then build the constitutive equation for a symmetric part that is symmetric sigma equal to the L state tensor times symmetric part of the displacement gradient, this infinitesimal deformation tensor. And I can build my variation formulation suggested by Reisner, which basically has a complementary energy, 1/2 of symmetric sigma dot C minus 1 times symmetric sigma, plus sigma dot nabla U minus infinitesimal rotation field. And this becomes a three-field principle, which depends on displacement, rotation, and the stresses. So if I take a variation of such a functional with respect to displacement, I recover from the upper situation, basically taking the derivative of this sigma, I will have a nabla, let's say, if I take derivative with respect to U, I'm going to have like a plus, then I do the operation that I shift the derivatives of U from sigma, I will recover something that is the divergence sigma plus F equal to 0, plus the interpretation of the Neumann boundary condition. If I take a variation with respect to a skew symmetric field, which is independent of rotation, I obtain from this one that this becomes a skew symmetric part of stress equal to 0. So these two are going back to the strong form of the equilibrium equation for the force equilibrium and moment equilibrium. Then I can take the derivative with respect to the symmetric part of sigma. I get back my constitutive equation from this one. And then finally, I can take the derivative with respect to the skew part of the sigma, and I get definition of the infinitesimal rotation field as the skew part of the displacement gradient. Then the work of Hughes and Bretzi being mathematician, where they handle this Babushka-Bretzi condition, that means ability to treat the mixed formulation and be able to introduce any convenient finite interpolation. They showed why do you need to regularize such variation formulation, and regularization happened to be with this regularization parameter gamma, and you add this quadratic form in the skew symmetric part of sigma. And basically the optimal value in their analysis of this paper turned out to be shear modulus. So intuitively it's kind of not so strange. So your regularized variation formulation with P index gamma becomes the one on top, minus 1/2 skew symmetric sigma dot gamma minus 1 times skew symmetric sigma. So you're really like regularizing this in terms of skew symmetric sigma, and as the upshot, as the advantage, you cannot take any convenient finite interpolation. So I'll show two. One is geared towards establishing the continuity with respect to structural elements, which are like beams, which have displacement rotation. And after that, we'll talk about the one that is interesting for dynamics, where basically the best approximation properties is reserved for statics. But if you go to dynamics, the same finite interpolation are far from optimal, and you have to kind of redo it completely and do much better work in terms of dynamics. So this is what I wanted to discuss. So with this regularization, it actually amounts to giving me possibility to provide a sort of constitutive equation for skew symmetric part of stress tensor as this regularization parameter, which we call shear modulus, and difference between skew symmetric part of displacement gradient and rotation. So basically, I'm taking now the interpretation of tensor rotation in some kind of weak form, giving me possibility to introduce this through the constitutive equation. So Legendre transformation would allow me to exchange the roles of sigma and u, and I can then reduce my variational formulation, which is regularized, to two-field format where I have only contribution of the symmetric part of the displacement gradient, and I now have a contribution of the skew symmetric part of the displacement gradient minus rotation through this regularization parameter, which is the shear modulus. So either this the mixed format or this displacement type of format could be a starting point of building my finite element interpolation. but this is now talking about these 2D problems. So again, this was the type of interpolation that you have for Timoshenko beam. So I take my isoperimetric element to represent, let's say, the two-node beam element that with the shape function that I built for the, let's say, parent element going from xi equal to -1 to xi equal to +1, and shape function being 1/2 1 minus psi and 1/2 1 plus psi. Then I build my theta and v to be done in terms of these shape functions. And then basically I built the approximation for the bending to be 1 over LE, LE being the length of the beam, theta2 minus theta1, theta2 to theta1 are two nodal values, and gamma would be v2 minus v1 minus 1/2 theta1 plus theta2 minus psi 1/2 theta2 minus theta1. So this is the simplest type of approximation. And basically I'm wondering what can I do in the simple problem. So let me illustrate that for the simple problem, I might have a difficulty using such a Timoshenko beam element. So here's the stuff that I'm actually studying. For example, I can take a cantilever beam and apply a bending moment at the end. So if I take any point x, with beam being from 0 to 12, I take this piece of the beam on the left-hand side and right-hand side. I should be applying the moment which I equilibrated. So from this one, I conclude very quickly that the bending moment diagram should be constant. M of x is equal to m. It's equal to constant. And then I have a CST constant. So I have a result that dm dx, derivative of the moment and the shear force together, that comes from the moment equilibrium equation, should amount to 0. So if this one is constant, this will be equal to 0, so that amounts to saying that V is equal to 0. In other words, the diagram of shear force is equal to 0, and I should have a shear being equal to that. So I take a simplest type of model. I take a simple two-node Timoshenko beam element, and I want to see whether I can deal with that. Well, it turns out that if I take a two-node beam element, and I make this theta2 minus theta1 to be constant, I have a problem to making sure that shear is equal to 0, because basically this is my approximation for the shear strain. And the problem there is that it varies in terms of psi. So I want to make sure that gamma is equal to 0 for any value of x or any value of psi. The best way is to say that theta2 minus theta1 is equal to 0. But theta2 minus theta1 is precisely the interpolation of my curvature field. So the only way I can have shear to be equal to 0 is if I also kill the bending. And so this is the kind of a locking phenomena, inability of the element to represent a pure bending mode for the rules that are kind of normally applied. So there are many remedies. We have a paper on that, giving a comparison of different remedies and ability to deal with the locking phenomena. Perhaps the simplest remedy of this one is so-called reduced integration. So basically, I compute this with the numerical integration, where I take only one integration point. So this one integration point for two-node Timoshenko beam element will use the abscissa xi equal to 0 and weight w equal to 2. And this will eliminate this contribution, so I don't have to worry about shear strain will then be defined directly from the nodal values of the transverse displacement V1 and V2 and nodal values of rotation θ1, θ2. And basically I can then represent the corresponding element. Or there's another way to deal with that. I can say that what really went wrong here is that given that I have V and I have theta defined as the same order polynomials, on the other hand, I had the shear strain to going back here was Timoshenko, the shear strain being the derivative of V compared against theta. Obviously, when they are the same interpolation polynomials, you can never match the derivative of something which is linear polynomial, which becomes constant, and the linear polynomial itself. So another remedy next to reduced integration is to pump up the order of interpolation for V And that's what you've done here. So basically, okay, if this doesn't work, you can add a bubble function 1 minus r squared times alpha. So it becomes like incompatible mode type interpolation for this. And then basically you can upfront eliminate this, let's say, contribution alpha, find the optimal value alpha by asking that gamma remains constant. So with such approximation, keeping the same approximation for theta, I can now recompute what is the gamma. So there's one part that's coming from compatible part, and there's second coming from this bubble function. So this is minus 2 xi, and then 2 L. So that becomes altogether xi times phi over L times alpha. And so if I want to now remove the shear locking, I have to enforce then this expression multiply xi be equal to 0, because this will remove the influence of xi on the approximation of my shear deformation. So this will be able to eliminate locking upfront. So by putting this term in the brackets equal to 0, I can then compute optimal value alpha to be equal to LE over 8, theta 1 minus theta 2, and I could put it back into this approximation. So then I start building the approximation of this displacement in terms of transverse displacement and the rotation. So it becomes, in some sense, close to just to remind you, if you probably studied it, if you didn't, maybe to give you this perspective. If you have something like a let's say Euler beam element, we have these two displacements and one rotation at each node. So typical interpolation of your V field, this V here, V of x, you have so-called, let's ignore this one, horizontal displacement. This is your V1, this is your theta 1. And on the other side, you have your V2. This is vertical displacement of the second node, and you have theta 2. So typically, when you're doing interpolation for the Euler beam, for transverse displacement of x, you use so-called Hermite polynomial. H1 of x will be something that takes a value 1 for V1, and then has a 0 value for the other V, and has 0 rotation here, 0 rotation there. So for 4 conditions here, you can build a cubic function of h of x, and you multiply, you say that your V of x would be equal to h1 of x times V1. Then you put, let's say, on the other side, you have a 1 value, then 0 slope and 0 value. So this will be your h2 of x. So that becomes plus h2 or V times V2. And then plus, what's also interesting, you have this rotation here, unit value. So this is 1, but displacement are 0, and rotation is 0. So that becomes something like Hermite polynomial of this kind. That becomes h3 of x times theta 1. And then finally, h4 of x. This is unit rotation here, 0 displacement there, and so on. So you have it like that. So plus h4 of x times theta 2. And so basically, you have a cubic polynomials, and here the curvature field in the Timoshenko bead, kappa is equal to d theta dx. And then basically your gamma, the shear strain, is equal to dv dx minus theta. So how do you get the Timoshenko, how do you get the Euler polynomial? You take gamma is equal to 0. With gamma equal to 0, you have that that your theta is equal to dv dx, because your cross section is moving along with the derivative of the transverse displacement. And then you take this one and you plug it into this term, and then you get this is your Timoshenko, and this is your Euler Bernoulli, that basically your theta will be equal to the second derivative of V with respect to x. And that is why you need something like a cubic polynomial and you have a linear variation of the curvature for two-node beam element and stuff like that. So you can reproduce all this with the Timoshenko beam, and that's actually in the direction we are going by using this type of interpolation where the transfer displacement field is not only a function of the nodal value of this transfer displacement, but also of the rotation. But of course, the interpolation gets a little bit more complicated than isoperiodic interpolation, but that's what the structures are requiring. They have reduced models, so reduction is certainly something that you have to take into account and accommodate this locking phenomena and do the proper modification. So how do I take the concept and put it into the membrane rotation? So this membrane is a kind of special membrane unit which has a rotational degrees of freedom. So I can easily couple this with the structure. So it has these two displacement here and this rotation. And then basically I start building it from the isoperiodic type of element. And so I'm taking the four-node interpolation for this isomorphic element. So this will be, X will be four shape functions, which are bilinear polynomial in natural coordinates psi and eta, multiplied by the nodal value of the displace of these nodes of the two coordinates of the nodes. And then if I want to generalize this type of behavior for the displacement, I'm taking the Timoshenko beam interpolation that we just devised with LEOA times θ1 minus θ2 times N3. So you can see that the way it's built. Here I take the first standard interpolation for the isoperiodic element that is four shape functions and I xi eta times ui that are the same ones used for the representing geometry. And now each and every of these sides is treated like a Timoshenko beam, where I filter the displacement component, which is in the direction perpendicular to the edge of the beam. And I make this dependent on two rotations parts. So that amounts to saying that here I have a NJK being the corresponding vector of union, unit vector exterior normal to filter out the component of this displacement, multiplied by the length LJK divided by A times psi k minus psi j. And so these shape functions become typical shape functions of 8-node elements. So these are now quadratic in psi, the linear in eta for the edges that are 5 and 7, and they are quadratic in eta and linear in psi for the edges which are 6 and 8. In other words, underlying element is not only 4-node element, but it's actually 8-node element. And I have these bubble functions that are typical of interpolation, just like in the Timoshenko beam. So basically now I have a membrane element which is fully compatible between Timoshenko beam and membrane. So I can take a full continuity between two displacement fields, one from the Timoshenko beam and the other one from the membrane, which is kind of handy. So the rest is just a straightforward application of the rules that we already discussed. Namely, I have my finite element interpolation. Well, actually, the other idea was this following. Instead of devising this interpolation, which is built following the Timoshenko type of beam, you can also do this in a much simpler way. That's simply that you enhance the displacement field with the incompatible mode that is reminiscent of the best choice for the 4-node element. That is, you take a bubble function xi and bubble function eta, and you act on that with the incompatible method. So this way you have a quadratic displacement that is kind of suitable for being used. And then I can build my, with the derivatives, so I can compare this against the linear interpolation of my rotation field. So when I'm computing the things like a skew symmetric part of the displacement gradient, I compare this against the bilinear interpolation of rotation field. Everything has to match, and I have no locking. I can actually enforce that this skew symmetric part of strain be equal to 0 without any difficulty. So basically, that is the idea. After that, you can either one of these two interpolations you can use, and you handle this element. These are some examples of the folded plates where we can kind of get the results which are, let's say, more or less perfect if you refine your mesh and so on and so forth. So this was the first story of building the incompatible mode element. And what I really wanted to recall here is the fact that you had a variation formulation, which is kind of non-usual in the sense that the skew symmetric part of sigma has to enter into the game in order to build the best performance of this particular element. So let me go back and see how this was useful for building the response dynamics. Namely, this is recent work of one of my PhD students who defended thesis only a couple of years ago. Basically, the idea is that we studied hybrid stress viscoplastic formulation, and we wanted to develop the elements, membrane elements for dynamics, which are able to represent the wave propagation problem. So let me skip that. I want to develop this mixed variation form for elastodynamics membrane problem. Plasticity and stuff we already studied, so I'll forget about that. So we come here. So basically, mixed variation formulation for elastodynamic membrane problem. The goal would be now to provide finite element interpolation, which are more useful for dynamics in the sense that you can represent the wave propagation problem. Let me go and illustrate this a little bit better. What I'm trying to discuss here is basically if you have let's say a static problem. This is your structure, whatever it is, and then a simple beam, let's say, and you study simply like a 3-point bending test. I can assume let's say this response will be I take these 4 3-node elements and 4 3-node elements, and I'm studying the static with this is bending and stuff like that. But that will be static. If I take the same thing and I do dynamics, and I take the same mesh, so this is my mesh here, and these are 3-node triangles, and I dropped now the weight, so that becomes dynamics. So this is like the same thing that I was presenting before with the that starts oscillating and things like that. So when you hit this, you have dynamics. Now you can say that in statics, you have static equilibrium equation, the weak form, and you know that the stress is optimal in each and every of those Gauss points. But this is also a constant strain triangle, so I take any of these triangles. So when the stress here, sigma of this element is a constant, so sigma E on this element, and the sigma E on the next element, this would be element E, and this will be element E plus 1, whatever is the numbering, doesn't really matter. So typically sigma E and sigma E plus 1, sigma E plus 1, E plus 1, are not the same. You have a jump because, this is a constant stress here, and this is a constant stress there. And at the boundary between 2 adjacent elements, which is this boundary here, you're talking about this line here and there, you have discontinuity of the stress with this kind of a jump occurring. So if you're now running dynamics problem and you have wave propagation and you have a stress is going from one type to another, every time you cross boundary, you're going to have a stress jump. So dealing with the stress jump, which is artificial, which is just the consequence of your, let's say, poor discrete approximation, because this is a constant strain triangle, so it cannot do better than making constant inside a particular element. You kind of certainly cannot do it. So my constant strain triangle is definitely the simplest one, and it's good enough for statics, where you have these, this is supposed to be straight lines. Sorry about that. Not easy to move this mouse correctly. So these are my nodes. The typical shape function, you have a unit value here, 0 there and 0 there, and it gives me the optimal value of my sigma, which is there. So my displacement field U of X is obtained as an interpolation of these 3 shape functions, NA of X times the nodal values of the displacement field. Let me call it dA. So then I compute my epsilon as the symmetric part of the displacement gradient of this, and I compute my sigma as a elasticity tensor times this epsilon, and I conclude that these are constant here. But if you want to do dynamics, this is not enough. So what we do, we build the hybrid stress approach, where sigma is not obtained like this, but sigma is computed as an independent type of approximation. Let me put it this way. Let's put it B times beta B, and we looked into that already. This is a function of X. So what you want to have, if you have this type of constant strain triangle, typically you take these b's to be middle of each edge. And then these betas are typical of these values here. And we want to make sure that if you have this unit vector of exterior normal n, that basically when you compute your stressed vector, Tn by Cauchy principle, being equal to sigma times n, that the jump in Tn, let me write it like this, is equal to 0. In other words, we want to have interpolation, which ensures you a smooth wave propagation going from one element to another when they are shared with the same boundary. So this is the game. I want to have at the end hybrid stress formulation where displacement and stress are interpolated independently. And this could be easily generalized not only for elasticity, but also for plasticity, viscoplasticity, and so on and so forth. And basically to enhance this behavior so that I can obtain a much better type of response for dynamics where the constant strain triangle is no longer optimal, because introducing these jumps in the stresses, it is giving lots of false information, my dynamics, and every time perturbs the wave propagation computation result, giving me jumps that are not supposed to be there. So basically, that is really the idea that we're trying to enforce here. So let me go into this, how we do that. First of all, we go back to the formulation of our membrane problem, where we have this force equilibrium equation, divergence sigma plus F. This time we are talking about dynamics, so it's equal to rho times acceleration. So as opposed to static problem of equilibrium, we have this dynamic equation of motion, where U and sigma and all that is function both of x and t. Then we enforce moment equilibrium equation, which says that the skew symmetric part of sigma is equal to 0. We can say the symmetric sigma is given by the elasticity tensor times symmetric part of displacement gradient. And we enforce the boundary condition, the Dirichlet boundary, impose displacement, and the boundary condition on the Neumann boundary with enforce fraction. Note here that the stress is not considered to be symmetric. So we can split now the non-symmetric stress into symmetric part, which is equal to 1/2 sigma plus sigma transpose. And skew symmetric part is equal to sigma minus sigma transpose. And then symmetric part is conjugate with the symmetric part of the displacement gradient, which is an infinitesimal strain. And skew symmetric part is conjugate to the skew symmetric part of the displacement gradient, which is the same as the infinitesimal rotation. So recall that any time you have a pairing between a symmetric and skew symmetric tensor, their scalar product is equal to 0 because they have equal number of terms but of the opposite sign, so they cannot cancel. Elasticity tensor is given in terms of lambda parameters, lambda and mu, and written here in terms of tensors, both of the tensors, second order the tensor product here, or in terms of the components. And recall here, these lambda parameters could be defined in terms of Young's modulus and the Poisson's ratio. So we've done this formulation already, and as I said, the regularization of this formulation goes to Hughes and Bretzi. What they suggested is basically is to be able to use any type of congruent interpolation. First of all, this is the Reisner type of formulation. We have a three-field formulation with the displacement, rotation, and stresses defined as a 1/2 complementary energy, which is symmetric part sigma times C minus 1 times symmetric part sigma, plus sigma scale product with the displacement gradient minus rotation and minus the energy of the external forces. For this case, sigma could be just square integrable. So it's the rotation. And displacement has to be in H1 to be integral with the first derivative to be square integrable as well. So regularization of Hughes and Bretzi is basically regularizing the skew symmetric part on top of the formation that I have above. I'm adding this term, which is 1/2. I don't know why Kongu changed it to rho, whatever I called this mu before, whatever is the shear modulus still, times the skew symmetric parts of sigma. That's skew symmetric times sigma dot skew symmetric times sigma. And then basically the corresponding variation formulation becomes this. If you take a variation with respect to displacement, here again, this kind of notation that I don't like. It's with little delta here is not what you call is just the name. So if U is the real displacement field, delta U is the virtual displacement field. So if you use Pierre, the delta U is Jean-Pierre, whatever, it's just the name. And so it goes for omega, with delta omega being virtual rotation and delta sigma being virtual stress. So we have delta U dot sigma n minus T bar being this imposed attraction of the Neumann boundary. So you recover the natural boundary condition, and you can also recover your equation of motion. If you take variation with respect to the infinitesimal rotation, you get the moment equilibrium equation that the stress skew symmetric part of stress should be equal to 0. That means you can force stress symmetry. And then finally, if you take a variation with respect to the symmetric part of stress, you get this formulation here, accompanying with a second term, which has a contribution of the skew symmetric part of the stress. Now, this term here, you can build it in a way which is enforced in the strong way. So previously we had this drilling rotation, so I kept my rotation because I needed them for constructing the Schreiner interpolation that can mix with the structures. At this stage for the membrane, I don't worry about that. I want to have a normal membrane, just conveniently interpolated for my dynamics. So to start with, I want to have what I discussed, this interpolation only for the stresses displaced and not to worry about rotation at all. So luckily, this equation here allows me to eliminate rotation. I can compute from here that rotation should be skew symmetric part of displacement gradient minus this regularization parameter times skew symmetric part of sigma. So plug it in back. This is just a reminder what is the external work. And then basically I have a different formulation where this sigma again is not symmetric, but I have a two field, something like a Hellinger-Rasne formulation, hybrid stress approach, with the independent field being the displacement and the stresses. So this is expressed as a 1/2 symmetric sigma dot C minus 1, C being a steady-state tensor, times symmetric sigma plus symmetric sigma dot symmetric part of displacement gradient. And here's this 1/2 the segregation parameter gamma, typically shear modulus, times the skew symmetric sigma dot skew symmetric sigma and minus external forces. So then I can take my variational formulation with respect to displacement. That gives me the symmetric part of the virtual displacement gradient paired with the stress tensor, which is not necessarily symmetric, minus the equivalent work of the external forces, that is virtual displacement dot F minus F being a distributed load, rho U dot double dot is equal to inertia force. And here you have a contribution of the imposed boundary traction. Then I take a variation with respect to the stress tensor, and I at the end have something which is written as the delta sigma. This is variation by stress, scalar product with the symmetric part of displacement gradient minus C minus 1. Let's say the corresponding constitutive tensor, which takes into account the contribution of the skew symmetric part, and that part is written here. So basically, you have this written as like C minus 1 ES minus C minus 1 times EA, where ES and EA are kind of symmetric and sort of skew symmetric part of a fourth order tensor. So when all is said and done, I have these two equations to treat, the equation for the displacement, equation for the stresses, and I'm solving this simultaneously in terms of the finite element method. So I do this transformation from the tensors, which I used up to now, to the vectors. So the formation is placed into the vector part. I have epsilon 1, 1, epsilon 2, 2, epsilon 2, epsilon 2, 1, and sigma 1, sigma 2, 2, sigma 1, 2, sigma 2, 1. Please now I take these four components because stress is non-symmetric. And then basically I had to build my interpolation. So displacement field is built in terms of the standard shape functions. I could use, and I'm using here, constant strain triangle to be a linear function. So then my strain is equal to B, which is the derivative of this shape function, times D. So these are constant computed at particular nodes. And then if I want to build stress interpolation, which are conveniently placed here, I'm using something called Rabier-Thoma vector space, where these shape functions have to be a unit value of particular node here on this edge, and going down 0 to the other two nodes. So that is kind of vector representation of my field, which is written here as the square root of 2 times psi and eta for the first one, then psi minus 1 eta for the second, and psi and eta minus 1 for the third. And I do transformation to the X space by basically this pure transformation here, such that the orthogonality of these shape functions is guaranteed. In other words, if you pair them in one node is 1 and the other two nodes is equal to 0, and all this is located. So this way I can build my interpolation for the stress field by using these interpolation parameters here. I call them tau, tau1, tau2, tau3 for the first component, tau1, tau2, tau3 for the second component, multiplied by these radiate comma vector space functions. And basically this is jointly written as sigma is equal to S times tau, where all these taus are put together. So basically such an approximation will give me continuity of the stress vector. What is stress vector? It's a stress which is defined by these two components. So either I can combine it with normal tangent part, or I can define the global part, which is kind of more convenient when you go along. So this way I have something that looks like a constant strain triangle, but it's actually better than that. It has straight edges, just like a constant strain triangle. It has a linear interpolation of my displacement field, and it has also the corresponding interpolation of my stress field, which gives you continuity of the stress vector from when you move from one element to another across this joint edge. So after that, I apply to this discretization. I come up with the two, let's say, set of equations, one dealing with the unknown values of the nodal displacement, the other dealing with the unknown values of the stress parameters. Please note that both of these equations are global because these values are shared between two adjacent elements. So the size of your problem becomes bigger. You not only keep the displacement components here, but you also have the stress components there, and then it becomes a significantly more involved problem. But the big advantage this way that you have is that the smoothness of interpolation of the stresses would eliminate all this spurious propagation energy that is typical of constant strain triangle when you have a dynamics and having a jump of the stress every time you cross the boundary between two adjacent nodes. So people were doing that before. They were putting just lots of viscous damping to kill it. But basically then you kind of have a two type of mistakes mixing each other. One is wrong interpolation of your stresses, and the other one is putting some kind of wrong viscosity to kill it, and then the end result becomes something quite uncontrollable. So here we actually enhanced the interpolation so that stresses are really possible to remain smooth in the discrete approximation, and then you have not this artificial introduction, these impacts every time you cross the boundary. So basically, we can integrate that with let's say midpoint scheme, and it was done here, and this typically can be done not only for the elasticity case, but we also study viscoplasticity case because we want here to long-term loading. In this case, so there's also the computation of the viscoplastic deformation. Why is it important to be viscoplastic deformation? If you want to have long-term computation, then we want to avoid using operator split, which is imposed in the classical plasticity. So basically, you can take a second order scheme and this type of conserving or decaying scheme applied and run it for a very long time. So this way, I can still use global computation when I'm computing my viscoplasticity, as opposed to being obliged to do it locally when I switch from viscoplasticity to plasticity. So here's a numerical example. This was done for dynamics, but this also happens to work perfectly well for statics, and not only simple statics, but statics when you have quasi-incompressible behavior. So a typical result are given here. This is your contours of the displacement field, and this is your stress vectors, because basically what you're computing here are these stress vectors all the time. So we just a little arrow is pointing here, which was the patch test for the quasi-incompressible behavior. So you can pass this without any problem. Here's a little bit more involved patch test when you have two different materials. Again, you can pass that without any problem. And then this is the bending. Again, this element is really perfect because it gives you like, first it converges from above, and it gives you very quickly quite an excellent result already. The course's mesh here, 12 times 6 is giving you, or the course of 6 times 1 is giving you a sizable better result than any of the others. This is concentrated triangle or 4-node element. And then here you already 12 times 6, you already basically exact towards the other guys take much more to converge and much more refinement in order to get this intent. But the statics was only part of the story we actually wanted, and this is now cantilever beam where you have this bending. Again, this one goes perfectly well, immediately converging, because it's suitable for this bending part, as opposed to the other guys that take much more mesh refinement, to converge. This is Cook's membrane problem, another reference type of result where you converge very quickly, and this guy certainly doesn't converge as well. Now, in dynamics, what we are doing is this energy conserving scheme, energy decaying scheme, basically that can take conserve energy as we go along. Once you finish this applying the impulse, then you simply can conserve energy. And then you can also play with a different type of triggering viscoplasticity and here and there, and still handle this. And then you have something with let's say long-term loading with the conserving energy. If you remove the let's say the plastic dissipation, there's no problem. So we were able to show that the computation can go into very long term, and then even you can do an energy gain scheme to handle, say, some kind of presence of high frequency vibration that could be typical of this problem. So this you can see that basically this non-conventional formulation, where you actually take into account the non-symmetry of the stress, would allow you not only to build the special, let's say, membrane elements that mix with structures to bring rotation field, but also would allow you to, when you limit rotation, to recover hybrid stress formulation that could be combined with any convenient stress interpolation. Particularly here, we chose this Rabiatoma. Rabiatoma, by the way, was initially suggested for the non-stationary heat transfer equation, which was a scalar field. And many people for a long time tried to make it work for vector interpolation like here, but turned out they always had this oscillation that was not really possible. And so basically what really removes this oscillation, this regularization. So that was a kind of big deal and worthy of this paper that you studied. So we did this for membrane, and we also did it for the plates. It's a kind of a little bit thing, but since we didn't talk about plates, I don't want to talk about that right now. So this is the second part here. So let me click out this guy, and I can start with the or I can rather carry on with the what we had this our beams, and we introduced the Timoshenko and Ole Bernoulli beam for this linear. But what is really often forgotten is that Ole did not study linear beam, but he really studied the so-called Ole elastica. They have actually a very large space and large rotation. So I want to study now the large rotation and large displacement. And let me start first by saying this, that you have like a 3D finite rotations as a key difficulty of this development. So basically 3D large rotations are difficult to study because they cannot be represented by vectors. They are represented intrinsically by orthogonal tensors, because 3D large rotation is basically preserving the norm of a particular vector. There's no deformation. And so you can say the deformation gradient has to be represented by the orthogonal tensor that is transpose, and the inverse of this tensor is to be the same thing. So the first fundamental paper goes back to Argyris, who was at that time the main editor of Computer Methods, Applied Mechanics Engineering, who made it very popular. Argyris was a Greek guy who was first professor at Imperial College, and then he moved to Stuttgart. He was head of the Institute of Aerospace Structures in Stuttgart. And when I was visiting in 1994 there with the successor of Argyris, his name was Bert Krupin. It was really impressive how big was the institute and how many things Argyris actually built. And so being the editor of this journal, he was able to write very long papers and nobody could stop him. Writing typically paper 10, 15, 20 pages is a norm of these journals. They don't like when it's too big because then they cannot sell too many papers. But at that time he could write paper, what is 155 minus 85, it's like 70 pages. So it's almost like a book. So he called this an excursion to large rotation to show how you deal with this large rotation and to see all the difficulties of this large rotation. So it was really a long paper with lots of kind of figures in color. At that time, it was the first time there were figures in colors, and they were all grouped in one place. And you have to study this a lot, and I did. And we did have lots of interesting ideas, but in terms of computation, still kind of made it a little bit confusing. So we worked on that, and some of these papers that are written here. So we actually figured out Euler represented the rotation in terms of Euler angles. These are three parameters. And making this three parameters, we also managed to put it like a vector-like parameters. So in terms of the representing this rotation, and I'll show you what it is. And then it turns out that these three parameters are never really unique. When you go over certain size, let's say rotation bigger than 180 degrees and stuff like that, then the parameters start being non-unique. And then you have to kind of build a better interpolation. So we had something called incremental rotation vector, so that you build on top of the orthogonal tensor. And then you avoid this problem of uniqueness because increments are not likely to be larger than 180 degrees. Otherwise, you have a problem with convergence. As it turned out to be kind of optimal performance that many people are nowadays using. There was a lots of work in that time with one of the joint work with Michel Girardin. We built a special issue of this journal. At that time was a DFN journal of finite element called Revue Européen des éléments finis. And we had this large rotational mechanics of structures and stuff like that to be there. So what is the difficulty of this large rotation? Here you have a large rotation and a small rotation. So large rotations are preserving the norm of a certain vector. And if you want to preserve the norm, that means that if x1 is produced by the rotation of the vector x, you take this to be a tensor lambda. And basically by putting that the norm of x1 is equal to norm of x, or you can say the norm square of x1 is equal to norm square of x, you can write this as x1 transpose dot x1. And this is equal to x transpose lambda transpose lambda. That means this is basically a lambda times x all transpose dot lambda x, and then you put this lambda on the other side, so it becomes lambda transpose. And then if you really want these to be the same, that implies that lambda transpose lambda should be equal to identity. In other words, lambda minus 1 is the same as lambda transpose. So this is your typical large rotation. And if in 2D, typically you write this in terms of cosines and sine. For example, if you take a plane and rotating a large rotation in the plane, and you put this axis 3 orthogonal to the plane, so you have a component here 1, and the other time will be, the other two will be cosine alpha minus sine alpha, cosine alpha. So you can see that lambda transpose times lambda will be identity tensor, and that lambda minus 1 will be the same as lambda transpose. If you linearize this, you get the small rotation business. Basically, cosine goes down to 1 when the angle is very small, and sine alpha goes to alpha when the angle is very small. And so you recover something called the small rotation. So infinitesimal small rotation, you can say that under small rotation, that would be lambda would be represented as identity plus w, where w is a skew symmetric tensor. So basically, the inverse of this identity plus w inverse would be equal to identity minus w, because these two combined will be identity plus w minus w, they cancel, minus w squared, but w squared is negligible compared to 1, so that is precisely equal to 1. And then basically, this is your skew symmetric tensor representing this type of thing. So here you have only 3 components which are unknown in a more general case, W1, W2, W3, and you can represent that in terms of so-called axial vector of this skew symmetric tensor, such that for any vector B, W times B as a kind of matrix multiplication vector B is the same as the cross product in the little w, which has components W1, 2, and 3, and the same vector B. So this is condition of the skew symmetry, and the same thing goes for a large rotation. Basically, each and every of these unit vectors that you take by large rotation from one configuration to another remains unit vector. So AI dot AI is equal to 1. You have these 3 conditions. And then orthogonality of this A1 to A2, A1 to A3, A2, A2, 3. It's another 3 conditions. You have 6 conditions. So 3 by 3, 9 parameters minus 6 conditions, you have 3 parameters. So strictly speaking, you can say you have 3 parameters, you can represent large rotation. It turns out you cannot uniquely, because if a very large rotation, the first choice was Euler angles, your pitch and draw, whatever, is that you can have a problem with non-uniqueness when you go over a certain value of this rotation, which then no problem for infinitesimal rotation field, because that really doesn't count. Why is it get stuck up? Ooh. Let me just see what happens with my computer. Why did it get stuck? Okay. So share screen again. How? There's another thing, another point. This design is a little bit, this picture is kind of messed up, but I can give you the stuff here. So imagine a little exercise. So you can clarify this one here, and let me do that. You can have a rotation along the axis in the over the, say this is your body, and this is sort of a long axis, and this is a short axis. Let's say this is rotation lambda 1, lambda 1, rotation around this axis here, and rotation lambda 2, rotation around this axis there. And then you can have like a fixed axis, that's the axis that are glued on the body, and the axis that are not glued on the body. So if you take a rotation first with lambda 1 and then lambda 2, so you're acting on some vector x. With lambda 1, you're producing, let's say, a vector x1, and then you're acting on this one and you're producing vector x2. And the x2 will be basically 2 successive rotations by lambda 1 and lambda 2. And I claim that the same x2 will be if you move this in the inverse order, lambda 1, lambda 2, but these are now around fixed axes, f and f. So I'll leave you this exercise because I said that the image here is messed up because at the time I didn't know how to motivate guys who were helping me build this transparency so that they produce this lousy type of picture. But this is the exercise where you're rotating some kind of elongated body along the 2 axes and basically show that they do not commute. You have to redo the proper order. And if you, on the other hand, a small rotation, you can do rotation any way you want. Whereas in the large rotation, you have to respect the order of rotating and how you do that. So basically one representation of this large rotation, it's in terms of exponential mapping. You have this exactly in this long paper by Giris, and you also have it in the books on dynamic system, a very famous book in Hirsch and Smale, 1972, Berkeley professors. So basically they have when you have this kind of a orthogonal tensor and you have a corresponding skew symmetric tensor theta, which is theta transpose equal to minus theta, as opposed to this lambda transpose equal to lambda minus 1 for orthogonal tensor, you can say that the large rotation has been built as a sequence of small rotations. So you can say that the typical small rotation would be, if you go back to this one, identity plus W, W being skew symmetric tensor, as opposed to large rotation simply being lambda. So I can take sequence of this small rotation to be identity plus theta, and to make sure theta is small, I take a small value epsilon. And then I simply take one after another. So if you have a just sequence, if you have like a really large rotation theta, but you want to make this into sequence of small rotation, you can build it as identity plus 1 over n times theta, being skew symmetric tensor, all to the power n. And then basically, if you let n go to infinity, that means little epsilon goes to 1 over n, goes down to 0, you can have the exact solution of this type of result. Namely, what you do there, you have this so-called exponential mapping formula, where the skew symmetry of theta is really the advantage to get the closed form solution. So this is done in this book of Hirsch and Smale, which says that lambda could be represented corresponding theta as identity plus sine theta over theta times theta plus 1 minus square times theta divided by theta by theta squared. So that becomes your skew symmetric tensor. This little theta is a corresponding axial vector, which places these 3 components into this vector notation. So you can say that you start computation by saying theta transpose is equal to minus theta. Theta times theta is called theta squared. Now theta to the power 3 could be written as minus theta squared times theta. And you can show this by using this vector identity, that if you multiply theta times v, this is axial vector theta cross v. And then again, cross this, cross that. And then you basically using the double cross product story, and you can kick out this one because these are 2 parallel vectors, and simply reduces to minus theta squared times theta times v, but that becomes again uppercase theta. So you show this one, then you go for the second term and so on and so forth. So basically then you're simply piling up, you find that there's a odd pairs 2k plus 1 is equal to minus 1 to the power k times theta to the power 2k times theta, whereas 2k plus 2, even pairs will be minus 1 to the power k times 2 theta to 2k times theta squared. And so you go one after another and you build your lambda. you do asymptotic development, then you recall what is the asymptotic development of sine function and what is the asymptotic development of cosine function. You conclude that your lambda is called exponential mapping or skew-symmetric tensor that you can write as identity sine theta divided by theta times theta plus skew-symmetric plus 1 minus cosine theta divided by theta squared times theta squared. And this is the exact result. So this is connection between the orthogonal tensor and corresponding skew-symmetric tensor as you go along, how you can build it. Another way, which was done by Ole when he studied that, he said, okay, in every large rotation, you have a rotation axis, which is not affected by the large rotation. So obviously, this has to be an eigenvector of your large rotation. So if you're computing the eigenvector of your orthogonal tensor lambda, you can set the eigenproblem as a lambda minus 1 times identity times the vector theta, or if I multiply through, this means lambda theta minus 1 times theta, that is eigenvalue equal to 1. And so the only vector which is not really affected by the large rotation is the one which is placed in the rotation axis. So what you call rotation vector is the one which is placed in the rotation axis. And this one can be characterized with 3 components, theta 1, 2, and 3. And so then when I'm doing large rotation, for example, I have rotation x, multiplying lambda by x to produce a vector b, the vector y. I can build this as a new position y. It could be built with a vector a plus b plus c. Here in the plane, when you cut it perpendicular to the rotation axis, you have your b, you have your c. And you can say that a is simply projection of x on the rotation vector. So this is x dot theta. B could be done with the one term, and C would be that term. So the way we did it is basically A is a projection of x to your rotation axis. B is x minus this projection times cosine theta. So this is x minus this projection that gives you there times cosine theta, because theta is this angle here. And then finally, the last one was theta cross x times sine theta. And so for this one, I can obtain that gathering all these terms that y is equal to cosine theta times identity plus sine theta times theta plus 1 minus theta divided with theta squared. That here would be theta tensorial theta times x. So please compare this as also another closed form solution for Rodriguez mapping, for the Rodriguez formula or exponential mapping. So obviously this is not the same. Here you have theta squared. The first two look the same, but that one is not. And basically here you have a tensor theta tensor theta. But you can again appeal to this double vector product identity and show that 1 minus cosine theta divided by theta squared times x is the same as 1 minus cosine theta divided by theta, theta cross theta minus theta squared identity x. And so starting from this one that you have here, using this identity there, you can recover the other exponential mapping. So either way you do it, what you have here is that you have a skew-symmetric tensor connected to the, let's say, the orthogonal tensor. Do I have here illustration? Hopefully here, for example, this will be the idea. SO3 is a sort of manifold. It's a curvilinear type of space that handling how you handle this skew-symmetric tensor. And then theta would be in the tangent space of the identity of this term. And then basically you can have a lambda as exponential of theta. That means here you travel in the tangent space, you have a straight line, and then you project down to the manifold in the way that you compute that the length of this is the same as the length of the straight line here. So this will be your illustration. What is the connection between the theta and the corresponding lambda? Now, if you want to say, I want to represent my large rotation with 3 parameters, I said there's already a problem. So it turns out that if you really want a unique representation, you don't want to go to 9 components of lambda, which is 3 by 3 matrix. The smallest number is 5. This was done in the paper of Stagnupel. But in fact, you can also pass with 4. These are called quaternion parameters of Hamilton. Basically, with you have this one, Hamilton type of quaternions, they have a vector part and they have a scalar part. And it so happens that if you have a quaternion, you can get unique orthogonal matrix. And if you have orthogonal matrix, you can have 2 quaternions. So you can set the computation in a way that you always use quaternion. And you only use a orthogonal matrix when you need it to build from this unique orthogonal matrix from this quaternion. So these quaternions are, this is your expression for your orthogonal tensor in terms of these rotations, theta and the axial vector theta. So if I take scalar part to be cosine of theta over 2, and vector pi to be sine of theta over 2 times n, where n is a rotation axis. It turns out that cosine theta is equal to 2q0 squared minus 1, and sine theta n tensorial is equal to 2q0 times vector part to be axial set. So I can write my orthogonal matrix in terms of quaternions with scalar part and vector part in a unique way. And this is kind of the connection for these type of quaternions. So this was also heavily used, and people are still doing with this quaternion parameter. So there are many things that to be said about this large rotation and papers that people are citing. For example, in robotics, they use it often and so on and so forth. But the big advantage of quaternion, you're kind of reducing the number of operations when you're multiplying two orthogonal tensors. If you have an incremental analysis, you go one tensor after another, doing different increments. So basically, in terms of quaternion, this is handled with smallest number of operations. The update of a scalar part is simply the scalar part of these two, minus the scalar product of two vector parts. And the new vector part is the scalar part of the first and the vector part of the second, and the scalar part of the second and vector part of the first, and minus the cross product of these two. And that's how you have it. And then basically, once you have this thing, you have to now worry about virtual rotation. So large rotation is orthogonal tensor. Virtual rotation should be infinitesimal tensor. So if you really want to mix this properly, you have to take infinitesimal tensor or infinitesimal rotation, put it through exponential mapping to bring it into SO3 space, and then multiply this with first real deformation, then go to the virtual deformation. But you can also have what you'll see in a moment, material representation, where you first go travel. So this would be your first travel on lambda, then you take a perturbation, the tangent space at lambda, and then you take exponential mapping, you come here, and this is your perturbed rotation. But I can also first do rotation, infinitesimal rotation, which is a perturbation or virtual strain, or virtual rotation, the initial configuration, then I travel lambda, I come to the same type of thing. So this would be like the idea. Now they're around fixed axis, and they can compare one another, and basically you have this type of result that is mixing one and the other. So there's lots to be said about this rotation. Let me see what I have to the end. Basically, that is when I go to the rotation vector, I can actually get this one. Basically, I can take the material formulation, and I can express my perturbed configuration that I do it in the tangential plane. And here I have immediately theta plus t times the variation of theta, both on my tangent plane. And then I take a projection, and I compare this against the material representation, which is taking lambda is exponential theta times exponential t times delta psi. And so basically from this one, I get that the variation of the material representation is equal to the material, let's say, variation of the this vector, and then you have like the same thing happen to be the t and lambda are sharing the same eigenvector. So this was done in this work that we done with the Ray and Elisa Kojar, and basically that they share the same eigenvector. That means they commute, so I can obtain the combination between the virtual rotation in terms of lambda and virtual rotation in terms of theta. So all is spelled out with this so-called commutative diagram. You can have many different parameterization of your rotation and stuff like that. So the whole thing of building these beam theories and geometrically exact is basically first you have to understand what to do with this rotation. Once you have this different type of parameterization of virtual deformation, you can go and build this thing accordingly. Just to show you that what you're able to do with such a development, you can build a beam element which is now geometrically exact. That means you can present this very large rotation in the exact way. So one of these benchmark problems was Barthe-Ballerucci beam, where they had to do it computing whatever 60 load steps. We can do that in basically 3 load steps and basically get really the same results without any problem. Here's something that is kind of nice to compute. If you have a pure bending beam, basically if you do it in a large deformation setting, it's very easy computation, basically because you take this is your beam. It's actually geometrically exact. So you put a moment at the end of the beam. You know that your bending moment m of x is a constant. So m of x is equal to m is equal to a constant. So if m is constant equal to m, that means the curvature, if I take properties of the beam, is equal m to divided by ei. And basically, this is also constant. So the deformed shape has to be part of a circle where you can actually preserve the same length, and you can build, depends what kind of model you put it, you can build it as a half a circle, you can build it in the full circles. For example, if you take this to be equal to EI divided by L, would be something times, let's say, pi. This will be this configuration here. If you take 2 pi, this will be this configuration there, and so on and so forth. So this is the type of element which can do that in single shot. And you don't have to have like many elements, you took 8 or so on, and you can get all these things. But this is very easy problem, this 2D version. The more complicated is if you bending at the same time and you're pulling it out of plane, then basically the problem with this SO3 manifold, this lambda parameterization, was that the element had non-symmetric stiffness. And if you really want to get the proper interpretation, you have to get this non-symmetry. Otherwise, if you take symmetric, you need many iterations, and you lose quadratic convergence. So basically, if you now have this rotation vector, you keep a symmetry, and then you basically can have it quadratic convergence with no big deal. And so this was the thing that we have developed. So maybe tomorrow we'll do this geometric graph beam dynamics and stuff like that, a multi-body system and all these things. So, and I'll show you maybe a little bit of this book, and we can wrap it up this way. So I stop sharing here.